I'm going to talk about the LCB2 that is Rapido that been developed at the University of Iowa and collaboration also with others. And I also got like the Ines Foundation that is found in my research. Excellent. I think that all of you have been impressed by the results obtained by because with 30 on data black bits, police has to Saturday Uvo in Alcagó. So it chess over abbreviation in general OP result immediately finance. So it was important to be able to obtain, I would say, superhuman performance. And of course, this amazing performance are particularly interesting, and so it would be particularly attractive to apply these algorithms to physical systems. But we are in a different setup because on one side we have people environments where we have a lot of data, where I'm not sure safety and so on. Instead of the physical systems, safety is an issue. Also, even collecting data is a problem because we all have appears to train our algorithm. And so the two key properties that people like to achieve with our videos are data efficiency and probability. Okay, so this is just really it's like trying to summarize because this is reinforcement learning. Actually, have an idea. So, the environment can be algorithm. So the algorithm applies textures to the system. It gets that observation, and so the goal is to apply the action in such a way that we minimize the cost of that. And the cost, of course, is a code, a task that you want to perform. So model 3, the reinforcement learning, basically is an approximation of the algorithm and optimize the actions directly on the system. Okay. I'm not going to elaborate the details, but since we want to achieve the efficiency, here we focus on model-based reinforcement learning, and that changes a bit the strategy in the sense that to extract more information from data that we collect in the system, we also build predictive model of the system. And the main idea is that in this way they can limit the experience and on the Apple system. You also optimize the policy on our model instead on the system. And of course, we can also use the model for kind of predicting the failure of our policy, so we use also for safety issues. Of course, the problem is that we need to build a predictive model system that is not trivial. So you see the outlines of our presentation. Since I'm going to, our algorithm is based on function processes. I'm just trying to refer to function process direction. Then I give an overview of the algorithm, and I present some results that we take standard from MathSparks. Finally, I will talk about the relevance and ongoing and future updates. Okay, let's start with Gaussian process regression. So, the main idea of Gaussian process regression is that we have an unknown function f that we want to learn, and we model this function a priori as a Gaussian process. This means that we have a prior beam and a parallel function. And of course, P also is a function of the state, and that the other function is so it determines the covariance of our Gaussian process. So the idea is that the kernel function is encoding the properties of our function f. Okay, so in some way it defines the similarity of f evaluated in different input locations, xi and xj. And so, as I told you, by playing with the function, you can determine the properties of our function f. So there are a lot of variables that you can use them to combine variables. So I'm going to review just two areas. The first one is the polynomial. So, and here you can see expression. And in this animation, you can see different functions sampled from prior with different values of e, so the degree would equal to 1 linear function, t equals successor function, and so on. Let's consider a very public error, but probably the most used one is the square exponential terminal. And I mean, here you can see expression. So here should be a minus also first. Sorry. The main parameter is this one. So the last case, okay. So basically, you have a negative exponential of the square norm included in a certain space determined by is as is. And again, here you can see some realization of that standard from Breyer with different values of that. Okay, and as decreases, you can see that you can see that the figures of another function have this. Okay, so what is important about this part is that through the kind of function we can in some way define the properties of f. So this defines the prior, but of course we need data to take f. And it there's a logical consideration that there are set of noisy measurements y. Noisy because we assume that so y is equal to f plus the noise. And from this data, this input output data, we can compute the posterior distribution that first, so is going to be quotient, okay? So we have a posterior mean and a posterior bias. The mean is going to be our estimate of f, is then the variance is some information about the confidence of our estimates. Okay, and of course it's in closed form, so this is a nice problem. So the expressions are not important, but let's try just to look at them, to draw some considerations about population context P. So first, the computational context T is dominated by this matrix inversion. So complex P scales with the Q of n, where n is the number of theta. But I just want to point out that, so this is the whole computational complexity, but notice that in practice we can recompute this matrix inversions from y, that goes to this inversion. And so at the end, the actual computational complexity at the evaluation time for the mean, so our estimate is linear with n, the number of eta, and for the bias is that it still stays in the cube of n. Okay. Okay. So as I said before, our algorithm NCTILCO is a model-based algorithm, and as almost I'd say all the model-based foster-Kerr algorithm, it accounts for 3 stages that are model learning, voice simulation, and then application curiosity. So these 3 stages are performing relative. Okay, so we start with some instruction data within the model. We optimize the policy on our model, then we apply policy to the system, we get new data, and so on, and then we start with the return. Then we introduce some notation. So XT is the stated type T, and since we're mostly going to work in the mechanical system, so the state is going to take account for Q that are the positions and Q dot the velocity. We have an initial state distribution about 0. UD is the system E, that is determined by policy I. And what's important to say about the policy is that it's a parametric function. So when we say that we are optimizing the policy, we are optimizing the policy parameter. And so, of course, the policy can be any parameter. We have the development task with C. That is in lobby the task that we want to perform, which is simply distant from the application. So, and we have the cumulative task. It's just the sum of the task over the testers. And so we are basically get final around in our program. We define J, that is a function of theta, that is the expectation of the cumulative cost. And of course, this expectation is computed with respect to the state distribution. And so the objective of the algorithm is to minimize J, so the expectation of the cumulative cost with respect to the policy parameters. Okay, now I would like to go through the learning NLP policy efficient steps just to give you an idea of how it really works. So in the model learning, we use all the data that we collect so far to build a predictive model of our system. So we are going to learn the function f that predicts the next state, so xt plus 1. Even xt can be, because of course you are assuming that our system is factorial. And share what prerequisites based on data, all the data that I'm for. And as you can imagine, we are going to use a function process selection. So at the end of the model learning procedure, the output of function process regression is just a one step ahead stochastic model that predicts the distribution of xt plus 1 given xt in the encoded values. So we are just obtaining a function f that predicts the mean and the variance of the next state. And those two are similar in next state distribution given xt. So seeing a bit that we have a little time, let me try just to zoom a little bit on the model learning. So we, in our opinion, we are considering each state dimension D independent, given xt and D. So we have a distinct P for each state dimension. The targets are neither plus date. Okay, you see, it's not choice. And so function S is basically trying to learn the data state. So as I said, there are first that is to define the prior, and the bounds is when you don't have strong prior information about your system. Generally, you set the b to 0, and you choose kernel that is able to approximate a y rate function, like the expression actual kernel. And so now is that I have commanded for so we have some parameters, so with lambda, L, so on. And the so version process regression allows to train these hyperparameters for one way by minimizing the negative positive boundary. Okay. So the second phase of model learning is the and reverse training. And then we compute the posterior distribution with the plus that nice making for. So okay, that matrix inversion that discussed. So of course we have to do it for every state dimension. And finally, we just have to combine these E's and B's to get the next, so yeah, the next state distribution. So since we are assuming that they are independent, basically we can sum the mean, okay? So the mean, yeah. And here the covariance is going to be just the diagonal areas with the GP's polaris of the diagonals. So overall, at the evaluation time, the computational complexity is going to be E times n squared because, yeah, for each TB we have to compute sigma is U squared, that is going to cost n squared. Okay. Okay, so it's not so complicated, but anyway, what is important is that at the end of the model learning phase, we have the one step ahead to test. So we have a mathematical tool that even text T and T provides us the posterior distribution that in ocean a mean and the co-rise plus one. And we know that the cost for this prediction is equals. Okay, so now we can go into the policy optimization phase. We say that this is the object function graph we want to optimize, and of course, so we want to compute the expectation with respect to the probability distribution induced by the G. So basically, for each time step T, we have to compute the state distribution. Yeah, and assuming that we know so the state distribution and capital T to compute the state distribution at that T plus 1, so we have to solve this two integral where E of xt, we here x tilde, that is the calculation of xt dt, comes from the motion loss integration. And this one is that is the currency in state distribution. So even assuming that the current state distribution is Gaussian, we can often do this integral closed form. Right? And so basically, of course, we have to rely upon approximations. Here we see that we have two options. The first one is moving matching, that is the one that has the explored. The good today is a very popular possibility. And here, so the main idea is that so we start from initial state distribution that is Gaussian, and under some assumptions on the order that you use and so on. If you choose that each state distribution is Gaussian, okay? Yeah, and so under some assumptions from the model, you're just able to compute the mean and the variance, so the first two moments, and that we match the moments. So choose that, so we set and force the one, the two, and so on, the Gaussian, and we just set the moments equal the one that carried. The problem is that, yeah, we cannot handle complex distributions such as bimodal distributions and so on. So this could be a too crude approximation of the approximation. The side of observability is that is the Gedau simulation. So the idea is just it simulates n particles and then compute these expectations, approximate this expectation with the expectation of particles. And the advantage is that so we have no restrictions on the kernel or the distribution and so on, but of course it's going to be more computational taxi. Okay, Renee. I just want to clear the difference into methodology. So, okay, here I expanded the our function, and so at the end, okay, we have to compute this integral, so the integral of the pos times the solidification of the pos first, and p the state probability comes from ABC, better that we say we are not a to sport. So the idea of model matching is to approximate this distribution with a notion with the mean and the variance equal to the mean and the variance of this integral value. And of course, if you are able to approximate, okay? And so notice that there is, if possible, compute the first and second moments, okay? Because could be unfeasible. So the take-home message is that here we add some constraints of this expression here, okay? Because it is sure that you're able to compute E, B, you cannot accept any more. And then we force the state distribution equation. Notice that also here it would have some constraints on the cost that we use because of first. So past that we get the state distribution to those part. So we also want to compute this integral with those parameters. So also we will have some constraints also on the cost. And so we start from a Gaussian distribution, we compute the cost, we apply mode matching, we get the next distribution and so on. This is to make matching it is obviously by vehicle. So the problem is that we are a postpone, so we can take into respect to theta. The two problems I would say that so we are forcing all the state distribution equations. This could be unrealistic. And of course, there are constraints on the GP model, on the policy, and on cost. But from three, you get choices that for sure you can apply. So you can use the RVF kernel, as commercial. You can use linear policy or a policy that is also a sum of exponential function. And as opposed to you can use the exponential. Of course, if you want to change the setup, you have to be sure that you are in this universe. So it's not real. Okay, so our algorithm in this status relies on the sampling days approximation. It is actually much simpler because the main idea is that so we start from the initial distribution, the sample and particles. Then for these particles, we evaluate the GP models, we compute the posterior distribution, we sample again, and so on. And we perform this operation for these steps. For each step, we have m particles, and we these m particles to approximate the expectation, this expectation here, within the sample of the total particles. So
the results. So of course we compare our algorithm also with state-of-art algorithms. So in particular, we considered other two algorithms. One is black drops, and the other is Pilco. So black drops, like MC Pilco, relies on sampling-based approximation, but is not using gradient for optimization. Pilco instead is using gradient-based optimization and moment matching. We use the cartpole to compare the three algorithms, and here you can see the evolution of the cumulative cost so the median and the confidence intervals obtained over 50 runs. And so I would say that, yeah, by comparing Pilco and Black Drops and MC Pilco, we can see that for sure, so sampling-based approximations seems much more effective than moment matching that probably is introducing some approximations, so too crude approximations that does not allow to converge in a consistent number of trials, of tentative. Okay, okay, now try to talk a bit about the developments that we are working on. So as I tried to highlight, one problem is related to the computational complexity, and that basically is related to the fact that we are relying on a non-parametric function, and so at the end, at each time that we want to compute the posterior distribution, we have to pay this cost. And so M, we can neglect it basically because we can parallelize over the particles, but so T is impossible. So what we would like to decrease is this N square, okay? Of course, we can use, what we are exploring is the use of approximated GP. So here there is a reference where you can see, so I would say is a very complete reference on GP approximations. What is important is that, so we start from the exact GP, and by approximating it, we obtain a parametric function. So we have a set of nonlinear features times a vector weight W, and we have a posterior distribution. Okay, so now our posterior distribution is no more on the function, but on the parameters. And so the idea that we have is that instead of sampling directly from the function, we can sample the parameters. Okay, and the advantage is that so through this approach, we sample just one time. So for each gradient step, okay, we sample a set of parameters for each particle, we sample from the initial distribution, and then the simulation basically becomes deterministic, okay? And so at the end, the computational cost that we obtain is T times D times P, where P is the number of parameters, and of course P is much smaller than N. And so this allows us to test our algorithm also in configurations where T is higher. That means longer confidence interval, longer intervals or higher control frequencies. Here you can see an application that we carried out in collaboration with India. So where we applied our algorithm to aerial robots. So on the right, we have a point-to-point task with a quadrotor, and on the left, a trajectory tracking with an hexarotor. This is just sim to real, okay? So we are still working on the application of the algorithm with actual data, because with this system, collecting actual data is really complex, and of course, also deriving a model as a consequence. We are also experimenting with locomotion tasks. So here you have I reported the results that we obtained with the swimmer. That probably is the most simple Mujoko environment. But for us, it was not trivial in the sense that we have a control. So we set the control frequency to 50 Hertz, and we have an horizon of 10 seconds, okay? So you can imagine that without approximations, this is basically impossible to be applied, so to apply our algorithm. And we compare it with two standard model-free RL algorithms that are Soft-Ator Critic and TD3. And here you can see the evolution of the reward. So the task is just go forward, okay? So the cost is minus the velocity along x. And here you can see the evolution of the reward, okay? And so at least to me, it was quite surprising in the sense that, so at the beginning, yeah, the model base is really not working well. But then there is a jump, okay? And actually, our algorithm reaches performance much higher than the one of the model 3. So we try to better understand this issue. And so here you can see the global mean square error. So this is a statistic of the model accuracy, okay? So we tested, basically we derived the model using only the data up to this time step, and we tested it on all the data. So when this global mean square error decreases, it means that the model is improving. And you can see that there is a kind of drop here, okay? And so the take-home message is that as soon as the model is accurate, performance drastically improves. Okay, I conclude briefly talking about ongoing and future activities. So we are also working on more advanced applications like the pick and throw. So why pick and throw? Pick and throw, so first of all, it has been already explored in this work here. So it's yeah, unlike pick and place, okay, in pick and throw, you pick an object and you throw it. The advantage is that in this way, you can enlarge the robot workspace, and also you can speed up the robot. But it's quite complex in the sense that to throw an object, you need a really good coordination between so the arm and the gripper. And of course, you have also uncertainty on the object, how you grasp the object, and so on. So in our setup, and also in the setup proposed in 9, the policy is just determining the release velocity. And also in our algorithm, it's kind of compensating the delay that there is between the gripper and the arm. So we collect data from 4 2D cameras of free motion, of the object in free motion. And with this data, we build a predictive model of the free motion dynamics. And yeah, really, so using just a few examples, we are able to get a good model. Because after all, the physics is not that complex. And as a consequence, so our algorithm was able to rapidly generalize to random targets. So this is what we get after, so basically 5 examples, okay? So this is the possible workspace, and here we are, so changing the target. So yeah, I think I skip to the next slide, okay? So ongoing and future works. So as I said, basically the challenges are to apply the algorithm on systems with more degrees of freedom, with higher control frequency, and so on, and industrial applications like pick and throw. And also we are working on contact-rich manipulation. Here you can see an benchmark proposed by Siemens. So pegging all, okay, with different complexities. And yeah, so we would like to apply the algorithm at the low level, okay? So to correct the robot trajectory online. So of course, this is going to be a much more complex task, at least in our opinion. So the question is how to improve the algorithm. What we are exploring is to power up the policy optimization phase with 2 possible strategies. The first one is to rely also on optimal control, since we have a model, so why not applying optimal control? And of course, also demonstrations. Okay, so that's all. Here you have all the references. I want to thank again the INES Foundation and of course also Mitsubishi that work with us.
So I'm going to talk about something that I've been working the last few years, which is autonomous skill learning and discovery, and you will understand what I mean. So one of my long dreams, which I'm very far away from, but that's my goal, is how to enable to do open-ended learning in robots. So we see little kids. I have 4 kids, so I watch them, and they can explore and find new ways of solving tasks, and it's very, very interesting and very, intriguing how we can take this behavior and transform it to robots so that they can learn from their own mistakes and, in a way, adapt and solve problems with very, very different ways. So if you give them a toy, they will find 1 million ways to to play with it. Not just one, not just the prescribed one, not the one in the instructions, but also many ways. And you see the same pattern in animals, in chimpanzees, in crows, where they can solve complex tasks using their creativity and finding novel ways to do stuff. On the other hand, when we're going to formalize, as Alberto said, and we want to see how we can learn from trial and error, the main and the prevalent formulation is reinforcement learning, which I'm going to skip because it's very well known, and Alberto said it very well. So we have the agent that interacts with the environment, it perceives some states, some observations, and it acts on the environment so we can, and we get to find our reward function, a loss function, which we try to minimize or maximize depending on what we want to do. And then in the end, we find a policy that can operate in the real world and find solutions. And with these approaches, we can do a lot of nice things, like what Alberto showcased, but also we can even see things that work on the real world and tough scenarios. And this is entirely trained in simulation, no real data, and it works on very complicated scenarios where the robot has to traverse in very confined spaces. This is not my work, this is from ETH, but it's very cool. With reinforcement learning, we can achieve very, very nice things. But behind the scenes, there is something that we're missing. So when we're doing robot learning, and everybody that has done robot learning on real systems will be familiar with this, we have some setups that look like this. So either we have too many sensors and cameras and equipment to do our experiments, so it's very far away from open-ended learning, or we have too many robots, so we want to replicate the parallelization that we get on simulation to get it on the real world. Or we have to teach the robot how to do stuff. So we have to grab it and say, okay, so now you have to do like this, and then you have to do something else. And this is very, very far away from open-ended learning and the robot taking intelligent decisions to actually discover how to do stuff itself. Also, another thing that is hidden, and usually it's in supplementary materials, it's that to make all these nice locomotion policies and other policies to work, you have, I don't know, it's like, oops, what did I do? Yeah. You have like, 2 or 3 pages, and they're very scaled down of reward functions and tuning the weights and how to find them. And if you change one of these weights, nothing works. So it's a very difficult process that is hidden below, but everybody that does reinforcement learning knows this, so that, you have to carefully tune your reward functions to find a good solution. Again, very far away from open-ended learning, where we want the robot to learn on its own and find interesting ways of completing tasks. Okay, so the last few years I've been working on something that we still don't have great results, but something that I think that is very interesting is how we can design pipelines that we have robots autonomously exploring to find new skills and then learning policies to perform these skills. And the key ideas that we have is that we need to somehow disentangle the problems. So if we try to solve all of the problem at once, it's a very difficult problem. So it's an end-to-end problem that most probably is going to fail miserable. And there are many attempts in the literature, and the results are not very good. So our idea is to disentangle the problems, and we split the problems in basically 4 main problems. So we have one problem is how we can have a robot that can autonomously explore all the possible things that they can do in an environment. We call this state space exploration, but basically what we say is that we have a robot, we have an environment, what the robot can do with this. So we need to find algorithms to explore what we can do with this robot in this environment. Then from all of these random trajectories and the exploration that we have done, how can we identify the important bits, what defines a skill, and how we can reuse things. So for example, we had a lot of, in a random environment, we can have an arm that does a lot of moving around. Some of them will grab a cup and do something, and this is an interesting skill that we want to keep. So how do we define skills and how we discover them from unstructured data is another important issue. Oops, sorry. Then, once we have the skills, we need to learn the skills. We need to learn policies that perform the skills, okay? And we need to learn policies that perform the skills well. This is the policy learning. And then the last problem is how do we transfer this to the real world? Because it's okay, we can do a lot of things in simulation, we can speed up things, but we have to transfer this to the real world. Okay, so our pipeline goes like this. We're going to use simulation as much as possible to do exploration. So we have the robots, we know them. We don't act like we don't know them, we design them, so we can have simulations and good ones. So we use simulation as much as possible to autonomously explore what we can do with the environment. Then we try to discover the skills from all these data points that we get. And then we use, I would say, classical reinforcement learning to try to learn policies that transfer to the real world and operate the data. Okay, so I'm going to explain all of the bits of the details a bit more and showcase some preliminary results and also future direction of what we can do. So the first, how did I do that? So the first thing that we're going to do, we're going to explain is how do we do state exploration. And the idea here, as I said before, is that we want to use simulation and we want to use deterministic simulation so that we can predict what happens. So we don't want to do stochastic simulation, stuff like that. We're going to exploit the mass parallelization that we have nowadays, either from CPU or GPU, so that we can learn a lot of things and get a lot of interesting behaviors. And most importantly, I think, we're going to use all the nice ideas from the evolutionary computation literature that usually people in machine learning do not know about, because there is a big literature in evolutionary computation how to do exploration and how we can search for novel behaviors and novel stuff, which is very interesting. And to connect it also with the workshop and the conference, we're not, how to say, fools. We're not going to try to search for anything from scratch. We have some models, we have some optimization techniques, so we can use also informed exploration policies, like, for example, a motivated controller, trajectory optimization that we can do so that we can find things that we can already do, that we know we can do, but also add these extra bits so that we can, how to say, allow the algorithm to find novel behavior itself and not be focused on specific stuff. Okay, then the other important bit is, okay, once we have all these trajectories, which basically are random trajectories. So we're trying to explore what we can do with the environment, and basically what we have here is that we have a robot that we have an algorithm that the main goal is to find new things. So it always tries to find new ways to explore the state, okay? So how do we keep from this all the important bits that define the skills? So our idea, and we're not the originators of the idea, but the idea that we like the most is that basically we want to learn policies that are not goal conditioned, that are latent conditioned, okay? So basically it's a goal conditioned policy, but we want to learn what is the goal, the latent space representation that we want to achieve. Basically what we want to have is we want to have a robot that we give it a state and we say, try to find what you have to do to get to this state, okay? And this is like a goal, but we need to find only the nice goals and the correct goals and not every possible goal, okay? So we define this latent space representation zeta, okay? And our goal is to learn this latent space representation zeta. So we have the states that we have seen from many, many trajectories, and we want to identify what is the latent space representation that is giving us a good representation of the state space so that we can use it as a goal condition policy, okay? And we're going to use variation autoencoders for this to learn it. And it's basically a representation learning problem, how we can effectively learn with data that we have so that we can, yeah. And then once we have this, then we can go back to traditional reinforcement learning, and we sample from the distribution that we have learned with the variation autoencoder, new goals, and then the reinforcement learning algorithm tries to achieve this goal, and we have a pipeline that we can close the loop. Okay? So basically, We do a lot of things. I will not go in a lot of details, but the idea is that we want to use all the data that we have for the variational autoencoding training, because then we have a more robust training and a better one. And an important detail that I will make more apparent later is that one would say, okay, you have the simulation, you have the environment, you know your robot. Why don't you do random sampling of all the states? And as I'm going to showcase, it doesn't work as well if we do random sampling, and I will explain. So we need diverse data, but we don't just need random data. It's a different process. Okay? And then, of course, as I said before, we do a lot of things like policies based on dynamical systems and prior knowledge, so that we don't just blindly find everything from scratch, because we have a lot of information, but we want also to be faster in this. Okay. And then in the last part, we do sim to real. So we want what we've learned in simulation, we want to transfer it to the real robot. There are many ways, things that Alberto also showed that we can use to learn models, to have prior models and learn models from some interaction and do stuff like that. In this talk, I'm going to showcase a different approach where we train entirely in simulation. We try to transfer to the real robot using something that is called asymmetric actor critic policy, so that we can effectively transfer what we know from simulation to the real world. Okay? So, another important thing, and to give credit to where it's due, our motivation was from this paper, where they were, in my, I'd say, from as far as I know, they were the first to do this disentanglement. So up until then, everybody was trying to solve the problem end to end. So we were trying to explore and learn the policies and find the skills all together. And then this came, this paper came, and they basically did this disentanglement. So they say that it's better if we explore the state, we learn the skills, and then we optimize the policies for the skills. We don't, if we do it all together, then we end up with things that are not really exploring, and we're not learning very well. But if we do it differently, then we can learn more effectively. And this is the idea that we're exploiting here in this work. Okay? Of course, in their implementation, they were using an algorithm for exploration, which is called state marginal matching. And then they were using a discrete latent space so that they have discrete skills. And then, of course, they were using RL, classical RL for skill level. So in our case, so this is a first implementation that we did, and to validate that our ideas work. Okay, basically we took this paper and we changed a few parts. So the first part that we changed is that instead of using state matching the SSM algorithm for exploration, we use the Go Explorer algorithm, which is an algorithm from evolutionary computation. Okay, and I will say more later, but basically we changed this exploration strategy to have, in our opinion, more effective exploration. Okay, and then the biggest change is that we use a continuous variational autoencoder, so we have continuous skills. We don't have discrete skills. So EDL, for example, was learning 10 skills, 20 skills, 50 skills, and you had to choose the number. And what we do here is that we don't learn number of skills, but we learn like a continuous skill that we can tune it, like one, two variable parameters that we can move and find new, change the skill set that we have. Okay, and then we do latent condition or goal condition RL to find, to optimize for the policies. Okay, so the main pipeline and the idea is as follows. So we have an environment. So for example, here we showcase a very simple mobile robotics environment. And we have this, the obstacles, and the task is that the robot is spawned randomly in one initial state, and it has to go to a random goal, okay? And in the end, we want to find a policy that we can go to any point in the space, but avoiding the obstacles, okay? And we don't want to give the information here to the robot that we know where the obstacles are. So basically, it has to learn on its own that there are some obstacles and we need to go there, okay? So first we do some exploration. So basically what we do, we start the robot from random initial locations, and we do random exploration using Go Explore, which is not exactly random, but using this evolutionary computation theory. And we explore the space, which is important and different from random sampling, because random sampling, what it will do if we do random sampling, it will fill all the space, even the obstacles, okay? But if we do exploration using the simulation, okay, we get what we call grounded trajectories, so they're grounded to the simulation, which means that only feasible things come up and not random things that might not be feasible. And this is much more helpful in when learning the skill discovery part. Okay. Then in the skill discovery part, we use the data that we collect in the exploration phase, and we learn the variation of the coder. And what we really want to learn here is we want to learn this latent representation zeta, okay, which we choose the dimension, how big or how small we want it to be, okay. And once we have this latent representation, basically, because we're using variational decoders, we can sample from this latent space representation, and we get new goals that we can use in an RL, goal conditioned RL pipeline to learn a policy that performs this task. Okay? So a few more details for Go Explore. The idea for Go Explore is that we have deterministic simulations when we can parallelize. And initially it was used in Atari games, but we can use it also in continuous environments and other environments. And the idea is that since we have deterministic simulation, what I can do is that I can keep all the interesting states that I've been to, I can return to them, and then continue the exploration from there. So I don't lose the information that I have collected over the course of my exploration. I keep it in an archive, and then I can choose wisely which new state I want to explore, that I know how to go there. Okay? So since we have deterministic simulation, it's very easy to say, okay, if I want to go to state 555, I know which steps I need to do. It's deterministic. I can replay them and reach there. And now, from this state, I can continue my exploration to do something better. This gives like pretty long trajectories, and most of them are like small macaronis, okay? But in the end, you don't care about because what you care about this procedure is finding all the possible exploration, all the possible things that you can do in the environment. Okay, and this is very important because then you get very good data to learn a good skill model, and then you can use it to learn good policies. So basically, you don't really do policy optimization. Okay, you're basically just trying to explore what you can do. Of course, in the original paper and extensions, you can also do policy optimization along with it, so that you can learn better exploration policy and do better exploration. But the main idea is that we don't primarily care about the policy optimization, but we care about how we can explore a space effectively. Okay? And then when we have the data, okay, the main idea, as I said before, is we want to find this compact representation of the state, this latent space zeta. Okay, which basically means that we need to compute these probabilities here, these distributions. Of course, this is intractable. We cannot do it in practice, okay, because we're missing some details, some things that we cannot really compute. And so basically, what we do, we approximate with neural networks, and basically this is the variational autoencoder. And what we do is that the encoder encodes the first bit of the equation, this distribution, and then the decoder, and then the encoder, and the decoder computes the other bit of the distribution. It approximates it. Okay. Of course, we do all the regular tricks that we need to do. There is sampling, the reparameterization trick, so that we can actually compute the gradients, similar to what Alberto said, so it's a good pass, so I don't have to re-explain it. Because you have to propagate the gradients, and because you need to sample, it's not easy, so you do all these, the same tricks apply. But this is standard in variational autoencoder learning. And the main thing that we have here is basically that we insert a state, we get a low-level, lower dimensional latent representation, usually lower dimensional, okay? And then we try to reproduce the same state, okay? And the important bit here is that once we have the algorithm has converged, so we learned from the data. What we get here is that we have this the optimal the way we have formulated it is that we want the target distribution here to be a normal distribution, 0 mean, 1 variance, okay? So if the algorithm has converged, then basically we can sample from this normal distribution, and then we get a lot of possible states. And what happens here is if you have good data and you do the training correctly, when you sample random from the normal distribution and you pass them through the through the decoder, basically you get back all the possible states that you can go from the simulator. So for example, in this example, here what we did is that we sampled from the variation of the decoder. So we learned from all the data that it has seen, and then we sample this latent space vector, and we get all these green points, which basically means that it has learned that here there's an obstacle that don't sample there. I cannot even reproduce it. And when I sample random goals, I sample basically all the green parts, okay? And this is automatically learned. We didn't tell it where the obstacles are, just from the experience of the robot that it couldn't go through the obstacles, for example, and the data. And the variation autoencoder could learn this, so we can generate targets automatically only with feasible targets and targets that make sense and not random ones that don't make sense. Okay? And then in the end, that's the most boring part, we use state-of-the-art reinforcement learning algorithms. Here we use TD3, but any algorithm could work, just random choice. And then given the learned variation of the encoder, we can define a few reward functions, how close we are at achieving the state or not, and we experiment with a few to see which one works better. And here we have a simple but how to say representative example. So we have a robot, here's a 7 degrees of freedom arm, that has a built-in controller that we don't know. That's the assumption here. Nobody told us what it's doing, so we can only give it commands. It's, I think it was 2 values, but it doesn't matter. So we can only give it commands. And what this controller does, it moves the arm only in this tube. It cannot move it anywhere else. We don't know this. This is a hidden black box controller. So we have to, how to say, to find a way to learn a policy that we can achieve any feasible goal, okay? So here we do go explore, and you see that all the blue dots are inside the tube, okay? And if we were doing uniform random sampling in the joint space, we would get results that look like this. So basically, the arm could go in any case. Because we know the arm, okay? We know our robot, and we can sample from it. But this is an extreme case where we don't know, we have some unknown that it affects the result that we can do. This could be, for example, a terrain or some physical capabilities of the robot. For example, a quadruped cannot fly in the air and move around, so it can only do a few stuff. Okay, so this is an extreme, but I think I represent the example that if we do random sampling, it will not work as well. So basically, that's what we try to do here. And what we see is that if we do our pipeline, so we do exploration with Go Explore, which is using the simulator and the black box controller, which we don't know, we cannot describe, but it's there. So we use the simulator and we get only data points that are good, so inside the tube, compared to using uniform sampling for goals and learning the variation of the coders. We get much better results, so our approach learns much faster. Whereas if we use the random sample, it doesn't work at all, okay? And as a comparison, because initially we thought, okay, we have a bug, it cannot work that badly. I mean, it's a random sampling, we have a lot of data, why does it work that badly? We did pure goal conditioned RL, so we used TD3 on the actual environment to try to learn a policy, and we see that it learns much slower if we do. And here, in the goal conditioned RL, we have all the knowledge of the state, so we know the state and everything. Is not like we're missing anything, but still using this exploration, using this, how to say, intelligent way of selecting goals for alert makes it to learn much faster. Okay, and we did the same in this environment. So we had the exploration part, we learned the skills, and now what you see is the resulting policy where we're sampling skills, we're sampling goals, any goal that, and it has learned to go around all the obstacles. And here it's important to understand that in the policy, we have no input observation of the obstacles. So the only observation is where I'm at, and it has learned to do this mapping. This is also an extreme case, just to showcase that we can learn this mapping to effectively select the goals that we have learned from the simulation. Okay? This is not important. So basically, this work was a validation that this approach, this disentanglement here that I wrote in the beginning, okay, can actually work. Because what we did is that we tackled state space exploration on its own. So we use an effective exploration. Then we use this data to do skill discovery. So we use state-of-the-art various coders to learn the skills. And then we use state-of-the-art RL to actually learn the policies to perform the skills. And this disentanglement, that this work is basically validating that this disentanglement works, and we can use it to do interesting stuff. So the rest of the talk, I will go in more details how we can insert prior knowledge in the policies so that we can do better learning, and also showcase some sim to real performance. So one of the things that is skipped quite fastly is that when we're doing exploration, we have a lot of data, okay? And a lot of them actually perform the task that we want to perform. For example, reach a goal or do some interesting thing, okay? So we can use this data to learn from demonstrations. And here I will showcase an approach that we developed to do so. But of course, and I think we will see more in the workshop later, we want to be safe and we want to have some guarantees about the policies, okay? So what we're trying to do here is to model a policy as a dynamical system so that we can do some analysis and find policies that have some properties. So in particular, what we want to do, we want to find, let's go back. What's the state is that if we use neural network policies, they're very good in the sense that they're very flexible and very generic, so we can learn any function and we can approximate any function. On the other hand, the state-of-the-art dynamic system policies, we can have stability guarantees, like asymptotic stability. We're guaranteed that we're going to reach a point whenever we start and stuff like that, okay? And they can also extrapolate well. So even in data that I have not seen, because I have this dynamical system or some model, I know what I have to do and I'm not doing random stuff, which is, important. But on the other hand, the policies have the different disadvantages. So for example, dynamical system policies, it's very hard to make them learn something very complicated, or it's much harder than neural network policies. And neural network policies do not provide these guarantees. And if you go to out of distribution data, then you have to pray that the system doesn't break. Okay? So what we propose is something that is in between. That's what we're trying to do, which is basically to provide guarantees. And if we are in a generic case, we cannot provide guarantees for all the system. So we at least provide guarantees for what we control and not for the rest of the system, which is important to have something. We have robust performance to out of distribution inputs. We are generic, so we can use any observation in any system, which is important, so we can adapt it to any system. And it's much more flexible than dynamical system policies. Of course, it's not as flexible as neural network policies. You have to lose something to gain something else. It's not easy to get it all together. And the main idea that we have is that we have a state, okay? We can split it in two parts. One is the controllable part, and the other is the non-controllable part. And the main idea that we do, and the main thing that we try to do here is that we want to guarantee things for the controllable part, no matter what the non-controllable part is. Okay, so we want to learn stuff so that we have guarantees about the controllable part, and the non-controllable part cannot affect the guarantees, but it can affect the performance so that we can do things. Okay, so that's the idea. So for example, examples of controllable parts is the end effector of a robot, the joints, whatever we can control, and non-controllable part is, for example, obstacles, objects, or whatever else we want to indirectly control, but we cannot directly control. Okay, so we model the policy as a weighted sum of elementary linear systems, and the idea is that we have elementary linear systems, which are classical. We have, for this work, a fixed attractor, but we can do stuff to remove. So basically, we want the policy to reach, we want the controllable part of the robot to reach a specific point. Okay, we have elementary systems, and we have a weighting function that fuses them. So the important thing is that we need to understand here what we want to do is that we can, using this policy, we can have specific properties for the A matrices that will make this to be stable asymptotically, so that we always converge to attractor no matter what. Okay? And what we do is that we use neural networks to model the weighting, okay? And then we can also enforce some constraints in this weighting, and we still have the stability guarantees. And if you are careful, what we do here is basically the controllable part is in the linear system, and then the whole state, including the non-controllable part, can go inside the weighting factor. So we have elementary dynamical systems that we can tune, we optimize for the A's, so we can find A matrices that do different behaviors, and we can combine them using information from the whole state. And you will see how this works, okay? And of course, I mean, I'm going to skip the details. We do Lyapunov analysis, and we showcase that in some assumptions which we can enforce in the optimization procedure. If this is always positive and this is the symmetric part of A is always positive definite, we can guarantee asymptotic convergence. Okay, and the general pipeline is like this. So the idea here is that we have this policy that basically is a dynamical system because it outputs the velocity of the controllable part. Okay, so the controllable part goes inside here. Then the whole state, including the non-controllable part, for example, here we have images, I will show you examples of images. It goes in the weighting function, okay? And then we compute a policy that is always asymptotically stable for the controllable part. So the controllable part, our robot, will always converge to the attractor that we want, even if in the middle we do other stuff, okay? And then we have this policy that we close the loop. Okay, we did a lot of experiments. Here I'm showcasing some examples in the LASA handwritten dataset. This is a two-dimensional dataset, which is very interesting because it has a lot of weird shapes. And we need to learn policies that converge on a tractor no matter what, but we also want to follow the shapes. And the resume that I'm showing here, SEDS is another approach that's learning dynamical systems. If we use pure neural networks, okay, you get very good estimation, but what you don't get is you don't get asymptotic convergence. So basically, if you start from a wrong point, you're going to end up nowhere, okay? Whereas when you use our approach, you still get very good approximation, but always get convergence to the points. So this is just to validate that what we're saying is true and it makes sense, okay? But what we can also do here is a multitask experiment, where basically what we have a camera on the robot. Why does it not play? Okay, so we have a camera on the robot that sees the wall, and depending on the wall, on what the wall shows, it follows a different trajectory, okay? So if it sees a line, it does a line. So it starts from an initial point and goes to a final point, it does a line. If it sees a sinusoid, it does a sinusoid, and we have like 3 or 4 of them, okay? And what we do is that we give one demonstration for each. So one demonstration, what you have to do in the line, what you have to do in the sinusoid. And the policy learns from these 4 or 5 demonstrations, I don't remember how many, learns how to do the tasks. And basically what is more important, as you see here, is that if we change in the middle of the task, in the middle of the execution of the task, it can follow the new task and it can do the new thing, which is very, very interesting and very important. And this is because we insert here the whole state. So, for example, this non-controllable part, which is the camera that sees what is the task that I have to do. It can adapt online and change the task. But most importantly, it doesn't affect the convergence, the stability of the system. Okay? Because we have proved the convergence for the whole system. So even if we change the non-controllable part, no matter what we do, we will always converge to the attractor, which is important in some applications. So basically here I have also the graphs, but if we use just a simple neural network policy, a convolution neural network here, and we change the task in the middle, okay? So it learns the task, if individual tasks, it learns them very well. So if you just let it, it will do it. But if you change the task in the middle, then you get behaviors that go to infinity and it cannot solve the task because it doesn't have what I want to showcase here that with this modeling, we can learn policies that have stability guarantees and work with observations that are not just states, so we can use any observation, even images, and do this thing. So we tried also on the real robot, we collect some trajectories, and we can fill the gap using only 3 demonstrations. And we generalize from many positions, and this is the same idea. And we can also do tracking of a trajectory. Here we have two RGB cameras that are looking at the line, and that's the input to the policy, so it has to track the line using the images. And it works in the real world, so we can use the policy in the real world and track the line, only with 5 or 10 demonstrations. And this is important to think. And I will end the talk with something that's ongoing work, and something that I think it's going in the same direction, how we can use information about the simulation so that we can do effective sim-to-real transfer. So the traditional approach to sim-to-real, and what I showcased, for example, from ETH, is that we do this teacher-student architecture. So basically what we do here is that we have a policy that is trained in simulation and knows everything. So we have inputs to the policy, the whole state, contacts, food, forces, and everything, okay? And once we have learned this policy, then we try to diffuse the policy to a smaller student policy, where we don't have all the inputs. So basically we have only proprioceptive or some IMU measurements and stuff like that. So basically we want to distill the teacher into the student and distill all the information that it has learned to the student. Okay, so this basically has this two-level optimization where we want to first learn the teacher and then the student. Okay? But there is another method that is very interesting that tries to do both of things together, which is called asymmetric actor critic, and it boils down to the idea that when we're using RL, we're learning an actor and a critic. The actor is the policy that we're going to use in deployment, and the critic is basically the Q function to approximate how well are we doing, okay? So the critic is never used online, only offline. So the idea of this approach is that we use the full informative state for the critic, all the information that we have in the simulation, the contact points, whatever, okay? So that we learn a very good critic. But in the actor, we don't give it the full state. We give it only what we have access on the real robot, okay? So basically, we learn together this, again, this information, what is important for the system, so for the actor to learn, but we learn together and we don't have to do this two-way process. Okay, so we develop an algorithm like this, and we do a lot of other things with some good skip. So we do curriculum learning so that we learn step by step, and we also do domain randomization so that we can transfer well. But the main idea is this asymmetric policy plus some informative reward functions, which are generic and not specific as the previous approaches, but I'm going to skip. And in the end, in the deployment, we don't have to use all the informative information, but we use only what we have from the robot, like IMU measurements, joint position, stuff like that. And the important thing is here, and then I will showcase a video and finish, is that if we use the normal way to do it, okay, look at the scale of the steps, okay, we need, this is the curriculum, so we go from the easy to more advanced and more difficult one. So we need like 300 million steps to learn a policy that can perform well on the real world. Whereas if we use this asymmetric actor critic and the informative reward functions, we need something like, I don't know, it's 140 million. So it's like half of the half of the computation that we wanted before, and we get the same quality policies. And then we can deploy this on the real robot, and we can see the robot learning only with onboard information. So here we only get the point clouds and nothing more, okay? And we can traverse steps, and we have new results that I do not have the videos yet, but we can even do bigger steps. Yeah, this is preliminary work that we're still working, but it's very, how to say, encouraging that we can do this pipeline. And of course, we want to merge all things together and put the pipeline that we explore, we find the skills, and then we learn them, and we have all this pipeline together. Again, of course, I want to thank collaborators, students and other collaborators from University of Patras. Now they are in France doing their PhD. Alexandros will go to Germany to do his PhD, so they were all undergrads when we did this work, and collaborators from UCL and University of Patras for making this possible. Thank you.
And today I'm going to present some of our work on incorporating safety and reinforcement learning. And before we begin, I just would like to make a wish for in this difficult times for peace and safety for everyone. Okay, so some of the applications that motivate our work. So this is our lab. We have a little robotics lab where we have cars, and we use human demonstration to learn trajectory planning, avoiding obstacles. So this is autonomous driving as an example where reinforcement learning is increasingly being advocated, but safety, collision avoidance is of course of paramount importance. We also work with architects on robotic construction. So this is we use reinforcement learning to come up with structures that are stable and robots can build them together. And here again, we must, if we want to really scale this up and have human-robot collaboration, we need to incorporate safety constraints. Another project that we work on with roboticists is robotic manipulation. So here we have a project that we want to use robots to do automated electric vehicle battery disassembly, or robots that can do manipulation. And so again, here still it's in simulation and verification, but safety will be increasingly important if you want to apply this with trust. So let's get right into the problem formulation. So we're working with a stochastic control system where state x t plus 1 is a sample from a probability distribution p, which depends on state xt and ut. And we have this classical stochastic control problem where we want to minimize an expected average sum of costs subject to our dynamics. And we know that classically dynamic programming has been developed to address this class of problem. You give the transition dynamics and your cost function, and dp gives us a set of optimality equations, conditions for finding the policy. So the policy is a mapping from the state to input, and it turns out that for solving this class of problems, it's sufficient to look at class of Markov policies just dependent on the state and stationary. And so over the past decades, our community has made a lot of progress to dynamic programming, for example, addressing more general objectives, safety reachability, multi-agent formulations, and computational tractability. Here you see an application of DP to trajectory planning for aircraft in stochastic weather regions. These are storm regions. We work with meteorologists to model a storm in aerospace and then use DP to plan trajectory modifications that are fuel efficient and avoid these stochastic storms. But a major limitation of DP is tractability. This is, despite decades of work, it still doesn't scale. If I were to put 2 aircrafts here, this algorithm would not be able to handle it. And also incorporating real-time data. On the other hand, we know that reinforcement learning has been a powerful approach for addressing the same stochastic control problem, where we now ignore or we don't model. We have a model-free approach, for example, and here we optimize the policy by interacting with the system. So the system becomes like a black box. We apply a policy, we observe the trajectories. We also have motivations about reinforcement learning and nice things we can achieve with it in the previous talks, and you also know that it's been really powerful in addressing some complex decision-making problems like chess and Go and protein design and so on. But safety, still having safety guarantees is an ongoing and open problem. And so I would like to focus on incorporating safety into one approach to incorporate safety in RL. And I want to also just acknowledge that this is a very active area of research, both from the reinforcement learning community, where they look at a constrained RL formulation, and also from control community, where we have different approaches of incorporating safety and constraints. And this is there are probably many more references that I missed, but just a summary of some that it's active and there are many approaches, and I'll present one approach towards this. Okay, so let's just get started. I'm going to talk about first RL objectives and safety, and then I'm going to talk about reinforcement learning for safety constraints MDP. Okay. So let's think about how in reinforcement learning or generally stochastic control, what are different ways that we can incorporate our objective. We know there's a finite horizon framework, so we have this summation is over a finite state, finite number of time steps, and the optimal policy in this case would be time varying, but still Markov. There is another approach when we look at infinite horizon objectives is discounting. This is very commonly used in RL, and discounting makes sure that this sequence, this series is summable, and also this gamma, which is between 0 and 1, gives us this contraction property in Bellman operator that helps really for algorithm design and analysis. And we also have an average cost formulation, which is another way to handle the summability of this infinite cost sequence. Okay? But what I want to briefly highlight is that even though discounting is the most used approach in RL, and there are many algorithms and software packages that use discounted or they're based on discounted RL framework, they cannot really capture infinite horizon safety, reachability, and stability. Average cost can, but we don't know yet very good and stable ways of learning, because whenever we are learning, we are using finite sample trajectories, and this is an infinite sequence, and we miss with average cost. We might have to wait quite long time to be able to see that those needed samples. Okay. So this is this discussion about discounted costs and its limitations. I want to be brief, but I want to be thorough, especially when I talk to an RL community. This I find very important because our community knows about stability and safety, but I think it's something that perhaps a little bit less known. And let's just highlight that before I go into our formulation. So let's just look at a discounted linear quadratic control. This, again, in our control community, we knew this problem, so I will be very quick. So we have a quadratic cost and a linear dynamics, and gamma is a discount vector in the spirit of RL discounted cost. And it's not hard to come up with cases where if you set the discount factor, you can have an unstable policy. Okay, because this discounting in a geometric way can make this cost to go to 0, to be finite, whereas the controller that you get out of it might actually make the system unstable. Okay, this is, I think in our community more or less is known, but it's more for the new generations that maybe just, or RL community just used to using RL frameworks. So here is, there is one of our colleagues who works on exactly characterizing how gamma should be so that we will have a stable stabilizing policy, but usually the right choice of gamma would depend on the actual dynamics, which in RL we assume we don't know. Okay? So this is a problem with discounted cost formulation. It's regardless of the solution approach. So if you see, for example, that you use a PPO or whatever package for RL that's designed for discounted costs, and you use it for stabilizing an inverted pendulum, and then there's all these sort of blogs that, oh, look, the training is not stable. The problem is not really well posed. This is not, the discounting doesn't handle stability problems. So I want to briefly highlight that. Are there any questions so far about this? So, okay, maybe this is obvious because we're in a control community, but now let's talk about safety and reachability. Okay, so safety is in our communities, we talk about safety, we mean that the state of the system always being inside a safe set S, okay? And when we have an uncertainty, we say that we talk about probability of the state being inside a safe set, and we want to design a policy that maximizes that probability. Reachability is about the state of the system reaching some goal set at some point. So there exists some time that xt is in G. And there are dual concepts, meaning that probability of being in safe set plus probability of reaching the complement of safe set is 1. So you can, if you want to find reachability for a set, you can solve safety for its complement and so on. Okay? So this is safety and reachability, a control theoretic view. So then we can ask, okay, what can safety, now suppose you have a safety or reachability objectives, could they be captured with a discounted cost framework? And it turns out that this is also not the case. Again, this recent paper from the formal method community proves that given some reachability objective, for any discounted reward, you can find a transition kernel such that the optimal policy for the reward will not be the optimal policy for the reachability. And they create this example. Basically, their insight is that by choosing these transition probabilities suitably, you can make sure that you will reach the goal in a very, very long time, but because discounting basically forgets about long-term behavior and focuses on near-term behavior, it will not be able to have a policy that reaches the goal, okay? And there are other examples also in these figures. So if we are really concerned with safety, stability, reachability in infinite horizon, I mean, stability is already an infinite horizon concept, this discounted reward framework is not suitable. So what can we do? When we thought about the kind of problems that we work on in the lab, like robotics and autonomous car trajectory planning and so on. And we realized that a lot of these are finite horizon. You just plan a maneuver or you do some tasks together. And of course, we also have safety constraints and reachability constraints. So we decided to, okay, let's at least just focus on finite horizon setting and see what we can do. And so let's just briefly define also finite horizon safety and reachability. It's very similar to before. So we have a stochastic control system over a finite horizon T, and safety says that given the safe set S, for all T in this finite time horizon, XT remains in set S, and reachability says that given a goal set G, there exists some time that XT is in G. And then we have this reach avoid problem that given S and G, we want to make sure that at some point there is this T that XT is in G, and for all prior times, X top is in the safe set but not the goal set. And this is reach avoid includes safety and reachability. Okay. So these are the type of constraints that I'm going to focus on. Are there any questions so far? Yeah.
The notion of reachability.
Yeah.
Once you enter into G, are you
Yes.
staying there?
Yes. So once you enter, then our goal is satisfied.
Then
Then we stay
okay.
there. Exactly. Yeah, that's a good question. Yes. Good. Other question? Okay. And then again, a more closer look at how the path works in RL incorporates safety constraints. So this is a safety gym. Is like a Python environment, RL environment that is exactly developed. It's from OpenAI and is exactly developed to incorporate safety constraints and test safe RL framework. But how do they deal with safety? They either add a negative reward for constraint violation, so W, this is indicator function of X not in S, or they have this sort of a discounted cost subject to some discounted negative, discounted cost for violating constraints. And both of these approaches require a lot of tuning and tuning of the weights or this sort of discount factor and so on. And they don't come with a priori guarantees on safety. And so the problem we wanted to solve was that we have this reach avoid constraint. So this is CSG is the set of trajectories in over time horizon. T such that at some point they reach a goal set and at all prior times they're in safe set, not in goal set. And we want to find this pi star that solves minimum over policy of this finite horizon running cost subject to probability of reach avoid being above some threshold. Okay? This is a classic, this reach avoid constraint has been looked at in our community. One of the early works was Abate, Prandini, Sastry, then Summers and Ligeros, and I worked on it when I was a postdoc, and then also some recent works about it. But all these works assume the model-based approach, and now we want to go into a learning-based approach. Okay. Questions? So this is a problem that for the rest of the talk, I talk about how we use reinforcement learning to solve this problem. And this is a joint work with my PhD student, Ting Ting Ni, and a former PhD student, Ilnura Osmanova, and my collaborators. And it's based on the results of these 3 papers. I will summarize. The latest one was in HSCC Hybrid Systems Computation Control just a month ago. Okay. So let's now talk about this RL with reach avoid constraints and how can we design an algorithm, learning algorithm that satisfies this. So let's now give a little bit of an insight into the problem. If we define history at time t as the set of states and inputs of our system, then we have different classes of policies, stochastic policies, a history-dependent policy. UT is a sample from pi t, which gives a distribution on the input space condition given the history. And then we can have a Markovian policy, which means that it's sufficient only to consider only the last state, xt. And then if this pi doesn't depend on time, we also call it stationary. Okay, so these are the class of policies, yes?
This T is long enough?
And for the problems I'm considering finite horizon long enough so you can do the maneuver. But this definition, I guess if you have infinite horizon, it would be really like hard to, as ht gets as the t gets large, it would be hard to keep track of a history-dependent policy. That's why we are usually after a Markovian policy. Does it make sense? Yeah. Yeah.
Stupid question, but reach avoid means so you have a safe set, and if your goal set is a safe set, which also would mean that the goal set is also safe, right? Like
Yeah, goal is subset of safe, yeah.
But my stupid question is why the reach avoid constraint? So because it means for me you go into the goal set, but then you go outside of the goal set after tau, right?
Mm-hmm. We assume the maneuver, whatever you wanted to do, is done once you reach, like think of a car making a left turn. You want to avoid collision and complete your left turn, for example.
Okay, so the goal, the path has been finished,
Yes,
and now I
yes,
can go back
yes,
to my
yes,
safe region.
yes,
Okay,
exactly.
okay,
Yeah,
good,
good.
thanks.
Yeah, other questions? Okay. So let's talk about, let's get intuition about our problem. So here is a constraint Markov decision problem. It's called CMDP, and it's minimizing some running cost subject to some running constraints, same type as the cost function, okay? And for this problem, it's known that the optimal policy is Markov, so it's not history dependent. And we also know that if we don't have the constraints, optimal policy is deterministic. But once we have constraints, the optimal policy is stochastic, okay? So the policy might have to randomize to balance safety versus minimizing a cost, okay? And now, but this is for a very specific, almost all the literature on CMDPs, constraint Markov decision processes, assume that the constraint is in exact same format as the cost, but this is not exactly a reach avoid format. So we ask, what about in our safety constraint MDP? And so we can come up with examples. So here's our safe set ABDE, it's just a 6-state dynamical system, it's a finite state. And there is a cost on state E, and the green ones are safe, and the U is the probability to go from state D to E, U0, and then U1 is minus U0. And we can just, with this, I have worked it out in the appendix, but you can show that the optimal policy in this case, when you have a rich safety or a generally rich avoid constraint, will be history dependent, because the policy would look at what has passed before to know how much budget it has for safety, okay? And that's the intuition about it. But this is not good. We don't want to deal with history-dependent policies. So what do? It turns out that we can reformulate the problem in a way that it becomes a classical CMDP. So I want to give a little bit of intuition about that. Any questions? Okay. So how do we go about this? So this is bringing in some techniques from automata specification and satisfaction. And the high-level idea is that we can introduce some finite state Q, 0, 1, 2. State 0 capture. So let me explain with this. This is our finite state machine. We start in 1, which means that we are in safe set, but not in the goal set. As soon as we go to the safe set complement, we go to state 0, and we stay there. We don't have a way out of it. But if we go to the goal set, We are now in state 2 of this automata, and we also stay there. Okay? Now we can, our original state space was x, our new state space is x times q, and so we just get an MDP on an extended state space. Our transition probability for x are as before, but the QT state of this automata is determined by what the trajectory of the system is doing and what QT was before. And then with this, so by this construction, we find that x1 to t, this finite horizon trajectory, satisfies the reach avoid if and only if at the final time qt, this discrete state is in state 2, because we were safe all the time and we reached the goal set. So this probability of being in this reach avoid set can be written that as expected value of the indicator function of automata state 2. Okay? So the probability of this set is expected value of this indicator function. And this now, in our extended state space, becomes like a final stage cost. Okay? So then we can show that the original problem, now for the sake of compactness, I removed the final stage cost. I just combined it in the cost from T0 to T. The original problem where we wanted the probability of reach avoid being greater than 1 minus delta is equivalent to a CMDP. Why? Because this is an expectation cost on a time varying running constraint. Well, from time t0 to t minus 1, the cost is 0, and at the final time there is a cost that's 1 when qt equals to 2. Okay. And also now, because that's a classical CMDP, we know that it's sufficient to consider Markovian policies, but on the product space of xt and qt. And this Markovian policy maps to a history-dependent policy in the original one, but it's not a problem because we solved that problem, so we get Markovian, so it's tractable, and then we can, because from the history of the state, we know which sets have been reached, then we can work out what that policy should be. Okay, any questions? Okay, so we went from a reach avoid constraint MDP to a classical CMDP, constraint Markov decision process over a finite horizon. And now we want to know how we can use reinforcement learning to solve the problem and have safety guarantees. That's what I will focus on now. Okay. So now this is our problem. Find the policy pi, which is a Markov. It depends on x and q, such that it solves this following problem of finite horizon cost subject to a finite horizon constraint. And our data is trajectories from the system for a given policy. We try a policy, we get the data, and we want to also make sure during learning the policies don't violate the safety constraints with high probability at least. So this is called safe learning. Okay. And how do we address this generally in RL? First, we parameterize our policy. For example, our policy could be modeled by a neural network. So theta t is the parameter of the neural network corresponding to policy at time t. And so then we are finding the optimal parameters for this problem, and that the difference between standard RL and our setting is that we also have this constraint there on the pi theta. Okay. And we apply a pi theta k, meaning that the policy coming from a neural network, we observe the trajectory and we want to refine it. And we want to design an algorithm that updates these thetas so that constraints are satisfied with high probability and converges to the optimal policy. So now this became our problem. Okay, so just a little bit more insight about policy parameterizations. So the one probably most familiar to us is the linear parameterization where pi theta, there is a theta transpose xq plus some noise, w, and this noise is in RL because we don't know the model, we always need to have some exploration noise. We can also have Gaussian parameterization, so pi theta can be a sample from a normal distribution whose mean is given by this function phi, some neural network parameterized by theta, and there is some covariance also that's non-vanishing to ensure exploration. So now we are searching for this optimal policy parameter. So our original problem here becomes actually like a constraint optimization problem. The reason is that we don't know the transition dynamics in the RL setting, so we cannot compute these expectations in closed form. But it is a function of theta. Our decision variable is only theta, subject to some constraints. Oops. But J and C are unknown, and they're basically, we want to learn them by doing zero-order queries of them. So this is exactly what I just said, because we don't know the transition dynamics, we don't know J and C in closed form, and this is now the RL, the safe RL problem we are solving. Minimize, it's a constraint optimization with J and C unknown, but only we can sample trajectories and try to estimate them. And we want to design a sequence, theta k, the algorithm gives us a sequence such that the constraints are satisfied at each iteration, and pi theta k goes to that pi star. So it's trying to find the optimal policy parameter, but it doesn't really know the safe set, and it doesn't know the objective. It just can query them and estimate them. Okay. So I give you an overview of our approach and go a little bit into details. So the idea of approach is to design a barrier. This comes from interior point methods in optimization. To design this log barrier that forces the iterates to stay in the feasible set. So the barrier grows to infinity as you approach the boundary of the set. And we estimate gradients of J and C using sample trajectory of the system. And then we take a very carefully chosen step along those estimated gradients. So let's go through each of these points. So this is the log barrier of the constraints. There's a couple of minuses just to make sure things are in the right direction, but basically it says that as C of theta gets close to 0, this one grows to infinity. And our unconstrained, now we have an unconstrained optimization, J tilde of theta is J of theta minus eta. This is our barrier parameter, log of minus C of theta. And we know that as eta goes to 0, the approximate solution, so the solution of mean over J tilde goes to the true solution, mean over J. And now this is our log barrier policy gradient approach. So theta k plus 1 is theta k minus gamma k, or step size, time. If we knew the gradient, it would be gradient with respect to theta of J tilde of theta k. This looks very simple. It's like, if you have seen policy gradient algorithms in RL, it's basically very similar to that, except that now we have a log barrier J, not log barrier of this constrained optimization rather than just having gradient of the J. And so we can ask, would this approach converge to optimal policy parameters? How to construct a good estimate of the log barrier gradient, and how to choose the step size for safety and convergence. And I'll briefly talk about these points. Yeah.
What happens if you start from an unfeasible?
Yeah, we have to assume we always start from a feasible point. Yeah, that's a good question. But basically, in any of these safety works, we have to, any of the safe learning works, the premise is that you have some feasible point. It might be not a very good point. You have some, some suboptimal policy, but it has to be safe. Otherwise, we cannot guarantee that we will stay safe.
If the optimal policies and other regions that you have to hop,
this, I think the hopping is not a problem, but for sure we have to start with something feasible. If we don't have a feasible one, we can try to minimize infeasibility failures, have some solve for some other objective to find a feasible point. Then we start running these algorithms. Good question. Yeah. Thank you. Other questions? Okay, so and these are basically the same type of questions in policy gradient in RL. It's asked, so basically we just generalize those to our log barrier constraint approach, but I will give you an idea of how do we address this. The first thing about suppose you go to a stationary point of this J tilde, is that an optimal parameter? It turns out that if policy parameterization is suitably chosen, then we have this so-called gradient dominance, which is a property that says, if you just forget about eta for a second and look at this gradient term, what it says is that if gradient of log barrier vanishes, so that last term is 0, J theta minus J theta star less than or equal to 0, which implies theta must be optimal because you're minimizing theta star is our mean. So this says that any stationary point is approximately optimal. This is the notion of gradient dominance, okay? And we can show that by proper choice of policy parameters, we have this new coefficient greater than 0, so we do have gradient dominance. And I want to give you a little bit of insight about how choice of policy parameter comes into play. So this brings this notion of Fisher non-degenerate policies. So it's a little bit of a mouthful, but basically what it's saying is that if you look at expected value of the gradient of log of their policy, this is just a certain transpose, it has to be lower bounded by a positive definite matrix. And there are some policy parameters that satisfy these, like Gaussian policy parameterization, Cauchy parameterization, and there are some policy parameters that fail to satisfy it, and the intuition is that there is no uniform lower bound on this expectation as policy gets deterministic. So this condition is closely related to how much exploration the policy is doing. So the more intuitive we can think of, the more random the policy is, the higher this mu f would be. Okay, and this means that we would have this gradient dominance property. Okay, so then this is basically consider basically your policy parameters to be smooth. This is not hard to satisfy. Just a second order gradients are bounded, and they have Fisher non-degenerate policies such as Gaussian policy parameterization. Then this is just basically spelling out those terms, extra terms that in gradient dominance come into play, but I want to give a bit of intuition. So J theta minus J pi star optimal policy is less than or equal to this. Eta comes from the log barrier. Then T is our time horizon, and G is the smoothness. Mu f was that Fisher non-degeneracy parameter. And then there is this epsilon bias term, okay? And I want to a bit highlight what that, so this is like a gradient dominance type property. Epsilon bias relates to richness of policy parameterization because we want to approximate the optimal policy pi star with optimal policy in the parametric class theta, and epsilon bias says how rich that parametric class is. So for example, if you have finite action, epsilon bias would be 0 for the so-called softmax policy. There are some policies like neural softmax based on neural parameterization. The deeper the network, this past work has shown the epsilon bias was smaller. So this means that how good your optimal theta solutions compared to optimal pi in the unconstrained space of all policies is depends on how rich that policy parameterization is. Okay, and this was known also for J being not a log barrier, and we kind of extended these results for our constrained RL framework. Are there any questions about this? Okay, then the next point is about how do we estimate the gradients of the log barrier, because J tilde is J minus log of negative C theta, its gradient would just be gradient of J minus eta gradient of C, or constraint divided by C. And so the idea again is that we have to use sample trajectories from our system to estimate these parameters. Okay? And because the cost and the constraints are expectations, we can use sample average to estimate them. Okay? Just use a sample average of the cost, or sample average of how many times we reach the goal set. So we can use J and C with sample average, and then we use the so-called policy gradient theorem to estimate gradient of J and gradient of C. So I briefly also highlight that. How many people have heard of policy gradient theorem? Maybe just, okay, a few. So I'll just briefly mention it. Just to get a little, of course, notation is heavy, but intuitive is not too hard to explain. So this is a finite horizon problem. So if we define the cost to go bt, the cost from starting at time t to the end of our horizon, then this is our cost to go. The policy gradient theorem says that gradient of Rj, this is just for the cost term, you can write it as a sum over t of expected value of the gradient of with respect to theta of log of pi theta times this cost to go. But the main point is that now, because this is an expectation, we can use sample average to estimate this term. So we put it together. It means that the gradient with respect to theta of j is sample average, so average over n samples. That was the previous one. This is just putting the trajectory points to do the sample average. So we can use sample average estimate for the gradients, and similarly for C of theta. And then we show that, okay, if n is sufficiently large, quite large, then you have high probability guarantees on how good are your estimated gradient to the true gradient. So with probability greater than 1 minus alpha, your estimated gradient, this one is within epsilon of true gradient, and you see how n scales with epsilon 1 over epsilon squared, with eta, which was logarithmic parameter, and also with basically this is our constraint. So it says that the closer we are to the constraint boundary, the more samples we need. This is what this is. So it just says, it just gives us a way to have accurate estimate of the gradient, but at the cost of a lot of samples. And then finally, the last thing, how do we choose this step size? And we know from optimization that gamma k should be sufficiently large to make progress, but sufficiently small to keep iterate safe. Because if we are inside a safe set and we only know our function locally, then we have to make a small step to stay there. And so we can choose, basically what we do is because we have measured the function, let's say the constraint function, we have measured it. We have some noisy estimate of it using sample average, so that here this is our estimate, and this is our confidence bound around it. Then, because the policy is smooth, then we can estimate quadratic upper bound locally around this point that approximates our function. And because we want to stay safe, we use this quadratic upper bound to define how big that interval that we can go can be. And putting this together, this gives us a way to choose a step size. And putting everything together, basically, this is the result we get for our policy gradient algorithm. Okay, so let's summarize it. We apply a pi of theta k, meaning a policy parameterized by something, let's say a neural net or something. Theta k is our parameter at time k. We get trajectory of the system. Then we update theta, we estimate gradient of the log barrier, but we do this many times to get a sample average estimate. We estimate the gradient of the log barrier, we choose our step size, and we then update theta. And there's how to choose this gamma and eta is exactly detailed in the papers. And we can show that the policies during this iteration with high probability satisfy constraints, so C of theta k less than or equal to 0 with high probability. We have convergence, so J of theta of t after t iteration is within epsilon of J of pi star, where t is of order 1 over epsilon squared, but per iteration we need this many samples to get this. Okay, so this is the type of guarantees we can get. Are there any questions about this? Yeah.
So the step size of the
Yeah.
is decreasing over time?
Yes, it's decreasing over
So
time.
you have the standard assumptions that must be
with some additional conditions because we want to make sure we stay safe.
And in any case,
It's decreasing, yes. It's like a mean of 1 over t and some other term that depends on the step size. Yeah, yeah. The standard in like a stochastic approximation. Yes, good question. Other questions? Okay. How much time do I have? I'm over. Yeah, I'm ending. I want to talk about verifying these algorithms. And well, this is a picture from Safety Gym. And this here you see some red robot whose dynamics we don't know, and there are a bunch of obstacles spread in the environment, and it needs to interact and find a goal set. I must say that it takes a lot of tuning to make this algorithm work, even for such a simple environment. And I have a control background, and I wonder, why should we do this? Why can't we just do control? But we want to learn and understand. So this is like of the order of 10 to the 6 iterations, interaction with the system. But this is our method with a lot of tuning and modifications. You see that this is constraint violation. It's much lower compared to a Lagrangian approach we looked at. And the rewards though are much slower, meaning the number of times you're successfully getting to that green box because of safety, we are very conservative and we're not exploring as much. This is the message. And this is in the lab, we also are implementing, so this is robot starts, these little cars or robots, and they start in random initial conditions and they need to find an exit without hitting these black regions. And again, this takes a lot of tuning, a lot of iterations, but it's, I think, for us at least, it was helpful to understand what are these class of policy gradient algorithms, what kind of theoretical guarantees they can have, and what are some limitations. Yeah, so this is somehow on some verification. Yeah.
here the reward of the unconstrained is higher.
Unconstrained, yes.
Yeah, but because we are not penalizing constraints.
Yes.
Okay.
Yes, exactly.
I mean, it's not.
Yeah. But
So
we are also
in
not
my
penalizing.
opinion, you should penalize also.
But we are also, the orange was a Lagrangian approach, so it's just a reward for reaching the green set.
Okay.
Yeah. And the blue is ours, which is, again, the reward for reaching green set, but subject to this, we do not want to violate as we learn.
Yeah, what I'm saying is that if we don't penalize reward.
Yeah,
So
for constraint violation.
Reward,
Yeah, that's
it
true.
will be always better.
Yeah. I see what you're saying. Yes. So yeah, it's work in progress still. I think I want to kind of come back with the beginning. Okay, first a few takeaway messages. This was sort of on the basics. Infinite horizon discounted cost constraints don't have a stability or safety or reachability guarantees. This is like maybe message one, but they are used in practice a lot. So it seems to work somehow, but we don't really have theoretical guarantees. We can have theoretical guarantees with finite horizon safety and reachability using this approach for example, the approach that I mentioned, but it comes at the cost of safe learning, comes at the cost of, can increase trust in training on the real system, but it comes at the cost of a lot of samples that we need a lot of interactions to ensure the safety and learning. So we are continuing to try to verify on the real world. Actually, this picture is from actually a linear quadratic control algorithm, because that has worked quite well for these applications, and what we want to compare with RL, how would it do? But as I mentioned, it's ongoing work. This is a new work, and it takes training is not easy. Okay, and we have been working on multi-agent system extensions. There are a lot of open problems in terms of existence of optimal equilibrium computation and learning. And regarding with these applications that I talked about, we haven't implemented this algorithm. The kind of algorithms we are using there are actor-critic type algorithms, which you also heard last time. Again, I think it's for me also to understand how does RL work, how does it compare with control. For such a test, we cannot use LQR, it just wouldn't make sense. because the environment is so complex when you're doing construction. There's a lot of modeling. But RL has really, I think, more promise to address these complex tasks. But then as soon as you go into like this kind of complex algorithms, safety guarantees become also much harder. So far we don't have provable safety, and it's a very controlled environment. There's other applications that I also talked about. Currently, we are using inverse reinforcement learning and reward learning, which is another challenge that was mentioned in the past talks. To try to implement it, we don't yet have like provable safety. Together with that, our safety guarantees for policy gradient, which because of computational scalability has not been applied to here, but this also gives us a motivation for continuing the research. And so yeah, thanks a lot for your attention. This is talk with my students and collaborators and my funding and my group. Thank you.
It's great to be here. Lately I've been hanging out more in the robotic community, so it's great to be back here in the control community. My PhD was back here. And today we are going to talk about indeed human-robot collaborative assembly. Okay, I got it. All right. So Mitsubishi Electric, it's also a factory automation company. And so we are definitely interested in the assembly problem, as you can imagine. But assembly doesn't happen only in industry. We actually also see it in our daily life, right? When we try to assemble furniture, for example, right? And even if we don't do it ourselves, most of the devices that we use, the computers, the phones that we use, they are all made out of some assembly process. And that's why we are very interested in solving this problem. And then the other component is, why do we want to put humans and robots working on the same work cell, right? So while I was preparing this presentation, I actually looked for the definition of human-robot collaboration. And of course, there is someone who thought about it, and the ISO standard defines it as a special kind of operation between a person and a robot sharing a common workspace. And this is kind of actually fitting for what we want to do, because this operation for us is assembly, or various forms of assembly, and we want to understand how two different agents, heterogeneous agents with different capabilities, can work together. When a few years ago I started working on this problem, the first question that actually our collaborators in another company, so Mitsubishi Electric Research Laboratories, we are the R&D lab of Mitsubishi Electric, right? And so then we report and we talk to Mitsubishi Electric. They ask me, does it really make sense to have human and robots working together? And if this comes with a surprise, because nowadays robots works very well in defined environments, right? And some operations that require too much dexterity, and then humans do it in a different environment. So how can we combine and put all of these properties together? So that's the purpose of the talk. And indeed, to achieve effective human-robot collaboration, I usually think about three dimensions. One is efficiency. Indeed, we want that, that the humans can contribute with their dexterity and also higher decision-making, while the robot can compensate with force, endurance, and accuracy. The other direction is safety. Of course, human physical safety is the first concern, but then eventually we want to allow to standardizations and also having safety of the robot and of the environment. And final is trust. That actually is not very much looked into our community, but I just started searching, and there are other communities that are very interested in this problem. Indeed, meaning that even if the robot is able to do the task well and it's safe, if the humans perceive that, it will still behave weirdly and will not be comfortable working with the robot. But just for sake of time, in this talk I will mainly focus on efficiency. So how can human and robot actually work well together? And just to clarify, some of the questions we are trying to ask is putting a human and robot will improve productivity, right? This is the final goal that we want to achieve. And the limits, as we were saying, are that robots work well in structured and engineered environment, which is expensive and it's time-consuming to build. Then we have cobots, right, that help a little bit in this, but then lower some other properties like speed and force of other robots. And then, of course, having humans and robots, the two different agents that speak different languages, then you have to add an extra layer of communication. Okay, so this is a graphic view, a little bit of the agenda of the talk of today. The idea is that we start from our initial conditions, right? We have let's assume we want to assemble a chair, for example, right? We start from initial condition, maybe someone give us manuals, maybe we have some videos, and we have a robot and a human agent, and we would like to give these initial conditions, make them work, and have the chair assembled at the end. So that would be the high-level goal. We are not there yet, but I will show you some of the steps that we did. And so I'll break down this in 3 parts. The first part is task filtering. Someone gives me these initial conditions. I want to understand what are the sequence of operations that the agents have to do. Once I have that, I want to understand how do the planning in between human and robots, in the sense that I have a sequence that possibly sequence from the previous part, but now I want to be reactive and adaptive. So I don't want to just have a kind of, it's called leader-follower paradigm. The human does this, then the robot does this, or something like that. I want to have a policy that closed loop tells me what the robot is going to do based on the current situation. And then I want also to understand how the robot does the specific skills required to do that, right? So, and potentially go over standard pick-and-place operations. And throughout this talk, in these different things, I will try to highlight where RL plays a role and it's helpful for the goal. All right, let's start. As in the previous talk, if you have any question, just raise your hands and I'm happy to answer. The first work is called Multi-Level Reasoning for Robot Assembly. It was published in April last year. And the idea is, again, we have some initial conditions. So we have the geometries and we have a goal. How can our agent reason about what we have to do in order to achieve our assembly, final assembly? We propose a method that is divided, it's called multi-level reasoning because we divide it in 3 steps. The first step is about inference of assembly sequence. We assume that we start again, that we have knowledge of the components and of the blueprint of the final assembled prototype. And we want to infer in which order, and so reasoning about the physical, the physical inferencing that we need to do in order to understand in which order we have to assemble these parts. For example, by looking at it as a human, I would understand immediately that this part has to be inserted after this one, right? I could not do the other way around. So how can we do that with learning? And the answer will be an implicit neural planner that is based on neural networks. The second part is that once I have this, I want to plan for what are the movements that each part has to do in order to do the assembly. And the third part is, now that I know the movement, how do I find the contact points at which I can apply a force, a magic tool can apply a force, so that I can actually follow the trajectory and do the insertion. Please.
Do you have a table or some graph with the relations of the objects? I mean, how do I know that the screw can be inserted in this mode or that?
That's great. I'm gonna briefly answer to this now, but basically in this part we did it by learning. It's a supervised learning method, and so actually,
so you didn't have beforehand something, you learned it directly from data.
We learned it all from data, exactly. So although my running more in model-based thing, this one is indeed just learning. It's going to be a big transformers. Some details are coming, not too much, but maybe I can give you more details afterwards. So indeed, the first inference is done through these part assembly sequence transformers. Basically, it works like this. So now we assume that we have cameras looking at the scene. We segment out the point clouds of all the parts and of the final assembled part. And then statistically, at each time step, we have these big neural networks that tell us which is the part that most likely should be assembled next. And then here we have, for example, the probability distribution, picture. So the highest one is orange, so we take the orange, then we remove the orange, and then we have the remaining 4. In this case, the highest is red, so we take out the red, and so on. Now, let's look at the details of what happens in here. For example, here we have 3 parts that are left, because the first 2 I already assembled, orange and red. And now, what do we have? The input to our, to pass the part assembly sequence transformer is the point cloud of the target assembly the point cloud of the remaining unassembled parts. This will go through some feature extractors. These are dynamic graph CNN. The features goes into a sequence of transformers layers that will predict what is the highest the probability of one part being the next one to be assembled. And interestingly, even if it's a harder task, we saw that the performance improved when we gave us an auxiliary task to predict also the pose, so the six-dimensional pose of the part in the final assembled piece. So first, inference of assembly sequence. Now this one gives us this graph that we saw before. So the first part goes in is this one, this is the second, third, fourth, and fifth. Once we have that, so now this is a given, now we want to find the sequence, the trajectory in order to insert that. And this one was done just with a standard planner. This is RRT Connect, plus some smoother on top of it, but nothing in particular, but it was already reasoning about contacts. But then the harder part was, okay, how do I actually move these components in where they should go? So we simplified in this way. First, we assume that we have an ideal branch, as if I am in the center of the mass of the object. That one is actuated, there is a magic actuator inside, and then I find the branch that will bring me along the trajectory until I arrive to the final position. Once I have that one, and that one can be obtained through simple controller plus gravity compensation, well, at least in simulation. After that, I solve optimization problems that, given this branch, will try to find the force at specific contact points that will be able to bring me there. How does it work? I have to optimize for two things here, the contact points and the forces. So for the contact points, I look to the whole surface of the object with a sampler. So you have to define a sampler that defines the contacts. There can be one or two contact points. So like one could be like one contact point because it could be pushing or screwing, or two because maybe it could be grasping. The sampler gives me these one or 2 points, and then I solve an optimization problem such that the force I obtain is within the friction cone of the object, such that I satisfy the branch that I have at the center of mass. By solving this problem, it's actually a simple problem that can be solved very fast, and this allows me to obtain the forces. That this magical tool now, that could be a gripper, or again a screwer, or just a stick to push.
Yes. I have a lot of questions, but I will stick to two.
Okay.
First, on the previous slide, I didn't get how you design the data set.
Yeah. So the
I
data
don't know
set.
if you're going to discuss it later or.
I can say now. Yeah, I have later. I have some videos of the dataset, so you will see it. But basically, we created a dataset. So we created a dataset based on some previous dataset. Actually, I'll answer to this question in 2 minutes because I have the slide.
And then the next question is, you say that you want to find the forces, which is good. I mean, but for example, how do you know that you have to screw and not push?
So
again, it's from the dataset. It's like
exactly the dataset. Exactly. So the parts have all the constraints.
Yeah.
No, thank you for the question. That's great. Oops. Yes. So this is the data set. Basically, to train this big neural network, we needed to create a data set that you see over here.
Yeah, I did this too. So you have to press it in the program.
All right. Sorry about that. By the end of the talk, I will learn how to use it. So this is the data set that we created, right? So this is an example of the assembly that we obtain. The yellow part is the kind of the blueprint, and then the blue part is the piece that we are assembling. And the green dot points are the contact points that you discovered in order to do the operations. This is based on Mujoko, and then there was already a data set before that we amplified and added all these constraints and contact points. But basically, it's a fairly large data set. It has almost 9,000 assemblies, and since for each assembly there could be multiple sequences, we provide in data set 85,000 trajectories for each of them. And this is an example of how it works. You see, for example, here, this is the first part, the second part assembled is the third part, right? These are the trajectory that we obtain, and those are the contact points that we optimize in order to do the operation. Okay, so this was the first part of the talk. So we have this kind of way to reason about the task and kind of try to infer what is the sequence that we can do.
The transformer network, does it only predict the part that should be assembled, or it exactly predicts the position, the pose of the final pose of the part as well? Because that, if that doesn't happen correct, for example, it goes just few millimeters
stay here. So the robot understands that something changed, and by default, in this case, it goes back to the home position, waiting for the state to change again and decide what to do next. So very quickly, was the completion time, and then so we did the experiment with 10 humans, 3 females, 7 males, and then this is the distribution of the completion time. So only humans or with robots actually, so the time improved, so we were faster. We asked them questionnaires about how their experience, and I'm running a little short on time, so I'll be quick on this, but basically we have that people found a little bit more mentally demanding the exercise, but in general a little physically less demanding. They felt a little bit rushed, but in general they felt they were more successful with the robot, and they were not afraid of the robot. So they liked working with the robot. And in the second questionnaire, they said that they worked well with the robot. They felt good in understanding what the robot was doing. So in overall, they appreciated the work and the help that the robot gave us. That is one of the main results that we want to achieve. Okay. Any question in this part?
So you have to do some training.
Yes.
But also with the human. How do you do the training with the humans?
It's a good point, but actually in this case it boils down to a very simple frame, because we can do everything in simulation, because so now the RL policy is just doing the planning, right, of the action. So there was not the physical. So we just have a simulator where we can simulate a human as we want, could be even just picking random actions, right? So it boils down to something very, very simple. Yeah. But of course we need to do the training for the hand detection and so on. All right.
There is no direct collaboration between the human and robot, like moving one object together, and everything is separate, right? And the human does its job, then the robot does its job.
Then I'm not sure I understand, but in this case, yes, we are just working on the planning side. So we are not modeling or trying to solve any dynamical skills, right? So that is not solved. But they do joint operations together. But this is also a skill that is learned separately, it's not part of this work, and is something that I'm going to discuss now. Let's see if I can quickly go. At a certain point, the human and the robot will take a piece of the chair together. But this is a skill that this planner assumes that is known and given by someone. This is just a planning side, right? Which action the robot should do. Like here they are doing it together. But the RL didn't define this policy.
Is it acting like a follower robot here, and the human is guiding the pusher?
Yes. Yeah. Okay. Final part of the talk, and then we are done, is the robot skills. So we started from task reasoning. We talked about planning and how the robot can react to the stochasticity of the humans. And now let's see how the robots can try to do some of these skills. So we tried, I will show you one, actually I have two works, let's see if I have time for that though, about autonomous robotic assembly. The idea here is how can we remove structure and assumption from standard assembly operations, and so how can we use sensor to make our robots smarter. Also published at IRIS 24, but this was actually also presented at CES, that is a big showroom in Las Vegas, so I had to work 100% of the time, or 99.9% of the time. So we started working on trying to assemble a gearbox, of course 3D printed, as simple. This was many years ago. This was actually learned using dynamic motion primitives. So we said, okay, we can already solve some fairly complicated problem, but of course, beside my very poor ability of doing videos at the time, there are a lot of fixtures, right? We had to build these fixtures, we had to put tape, we had to fix the fixture to the table, and so on. So we want to remove this kind of assumptions that are time-consuming and costly. How do we do that? Well, so first, what are the problems? Contact dynamics are hard to model accurately, and then to use them in planning. So this is one problem. It is difficult to sense, in the sense that when you grasp something, if you're using vision, then you start occluding it, and if you use tactile sensor, they are only very local to what you are grasping. So how do you combine these multimodalities, and how do you interpret and parse all the signals? And plus, learning in AI just purely requires a lot of data. So for our robotic manipulation, it's actually a hard problem because you don't have enough data. So we are trying to move toward this intelligent robotic manipulation, and this was an example. So now the idea is this one. We start from different location of these 4 components, just randomly put inside this perimeter, and we want to obtain finally an assembled gearbox. And this is an example. So the components are randomly put. Now we have an RL policy that decides in which direction they should go for affordability. So there's affordance matrix that decides. Affordance for grasping. Now, for example, now they were far apart enough, the robot decided to pick the first peg and inserting it. Notice that here on top there is a camera that you don't see, and here there are tactile sensors. The problem is that the peg is laid down horizontally, so you cannot insert it if it's in the final hole, right? So first it does a pre-operation that it puts it vertically, then it grasps it. When it grasps it, it does pose estimation using the tactile sensor, and then does the insertion. The insertion is done with an RL policy that uses the force torque sensor that is up here, and feel the contact and pushes it in. And then finally, in the end, even if it was assembled, as you see, the gears were not meshed, they were not aligned, so it went down and pushed again. So in here, we use for some component. So the reason why I show this one is that because when you do real assembly for something pseudo-real, you can just think that RL or any AI will solve the whole problem. So we use our L in some specific operation that were hard to model, right? Like the insertion, like the policy to opening spreading out the components. But then other things we're just doing with either optimization, trajectory optimization, or even, well, in this case, the sequence of operations was actually predetermined. But the idea here was, how can we remove, there are no fixtures, there are no jigs, but there are more sensors, camera, force torque sensor, and tactile sensor, in order to compensate for these inaccuracies. Question on this? Two more minutes? 2 more minutes.
Just
Finally, to conclude for human robot, how can human help also in learning of skills is, let's assume the idea here was we have some policy given, and in this case we are using diffusion policy. If you don't know the diffusion policy, they are super powerful right now in robotics, they're famous because they are multimodal and they actually solve a lot of real world tasks. First time I read about diffusion policy, they look magical, but basically, eventually from random rational knowledge, they can give you this multimodal policy. But they require a lot of demonstrations. What if a human wants to add his preference and change slightly the policy? So for example, this famous push T, right, where the focus is to put the T on the green shadow, right? Since this is a multimodal policy, we learn to do it in both cases. But let's say that now I have a constraint and I don't want the pusher to go in this direction. How do I change the policy? Or if my task was to stack this object, but they are stuck and not well aligned, and I want to improve their alignment, how can I enforce these extra constraints? So that's what we start doing. And so this is high level the method. Someone give us a diffusion policy or any policy, and now we want to use RL. To use RL, we need to have a reward. So we did it by preference-based reward learning. So the policy will start doing some rollouts. Then we give these multiple rollouts to could be a human or could be actually a visual language model that has some preferences, right? And basically, given 2 rollouts, it will tell us, oh, I prefer this one over this one. So just a binary reward. Out of that, we can extract a continuous reward, and then we will give to our RL to fine-tune the parameters of the original policy. It's fairly simple, the idea, but then the math gets a little bit more complicated. But basically, the idea is also that at the end of the day, this is a policy gradient method that Mariano already described, so that's great, I don't have to describe it. But basically, at the end, when you write your post function, you add also a constraint that is based on the KL divergence between the pre-trained diffusion policy and the new policy that you are trying to train with your reward that has your preference. And this helps in obtaining the new task while not forgetting the previous task. Otherwise, you would risk to forget the task. And here you can see, for example, some examples. So this was the pre-trained policy that was going in one direction, and the fine-tune goes through the other direction. Here you can see the rollouts on how it changed. So we were able to completely switch from one side to another. And the same here, this is the task stack distance. If you see the center of mass now of the cube is much closer to the center. And here, well, this is just the final, you can see that we are much more aligned than the original policy. So these kind of improvements, now we exploit what someone has already done using a lot of demonstration or a lot of training, and we can quickly adapt to new things. And for the purpose of human-robot collaboration, we actually improve the performance with customized to what our customer wants, right? And with this, I'm going to conclude. Sorry, I mean, I'm a bit late. We have talked about three things: task reasoning, inferring the sequence, planning, robot and human collaborating together, and finally, how to compute some of these robot skills in autonomous assembly and including the human preferences. Thanks for listening.
So the work I'm going to present today is joint work with Professor Sebastian Gros at NTNU in Trondheim, Norway. And it's about trying to put together two words that are apparently quite separated, which is model predictive control and reinforcement learning. And the idea is to try to get the best out of the two worlds. So usually I start presenting a bit reinforcement learning because people don't necessarily know it. Maybe you know it very well, but still let's go quickly over this. So reinforcement learning is essentially a way to solve stochastic optimal control problems, which they call Markov decision processes. And so it carries many similarities with dynamic programming, except that instead of propagating these value functions or policies exactly or numerically, let's say, it does so based on sampling. There's both model-based and model-free versions, and I think the winning point of reinforcement learning, among others, is that it accepts that it doesn't get the optimal solution. It gets approximate solutions, but often these are extremely good. And by accepting this approximation, RL is able to do things that we were not able to do otherwise. So it's a bit cross-disciplinary because it originates in computer science, but as I said, it has a lot in common with optimal control and also with system theory in principle, even though you don't see it explicitly usually. But also a lot with the statistics since it's based on sampling. And there's some really nice success stories. Maybe you've seen the videos of the aerobatic helicopter flight that was not really just reinforcement learning. It's a little bit different, but it's still in the family. Maybe more stunningly, it was able to beat chess, shogi, and Go masters. The Go community was shocked when a computer was able to beat the 18, I think he was world champion for 18 times, Lee Sedol. Even more stunningly, a few years after, reinforcement learning learned from scratch how to beat the best Go algorithm. It took 1 month. For chess, chess is a much simpler game than Go. So for chess, it was a matter of few hours to beat the best chess algorithm available at the time. For Go, it took 1 month, and it was able to beat essentially a simpler version of the same algorithm. There are some limitations. So some of the algorithms need some more development, but here I want to focus really on introducing guarantees, because when you do reinforcement learning, typically you get a black box, you press play and hope for the best. And if it works, it can work stunningly well, but it can also fail miserably. For instance, one of the working assumptions in reinforcement learning is ergodicity. So essentially, some form of stability. Try to apply reinforcement learning on a linear quadratic regulator. Very quickly, you will see that in many cases, your policy becomes unstable, and then off you go. The algorithm doesn't work. So your conclusion is reinforcement learning doesn't work. Well, no, it just requires some assumptions, and they are not always made explicit, and we should be aware of them. But for sure, you don't have any guarantee about stability, safety, or anything else. You're not able also to explain why you pick that action instead of another one. So we wanted to work a bit on this topic. So that's the focus of this talk. So just a bit of notation. Usually we write dynamical systems in this form, where these are the states, these are the actions. Here I'm taking the American notation. They didn't like X and U for some reason, maybe because U comes from Pontryagin, it's sometimes in mathematics it's Y, the letter, because it's the Russian letter for U. And it's upravlение, I think it's called, which means control, command. So Pontryagin used that. I like to think that the Americans thought, okay, we did the reinforcement learning, so it's an action, so we call it A. I don't know the true story. It's just okay. So just instead of X and U, it's S and A. W usually we take it as some random variable. But it's really more practical to write state transition probability. So rather than in this form, it's the same thing, just a different point of view, right? This defines the probability of transitioning to S plus when starting in S and applying action A. Of course, depending on context, this can be a probability density, a measure, whatever you like. And then another thing that is maybe a bit surprising for us, unless you do games, is that the policy is often stochastic sometimes stochastic in reinforcement learning. Of course, a deterministic policy is a special case of a stochastic one, but usually when people talk about stochastic policies, they really mean with non-zero probability for all states and actions. And what you want to do is to usually you maximize a return. Here I write it with a cost just to be more consistent with what we usually do. This causes some issues in some of the nomenclature, but it will not affect this talk. So essentially you want to minimize this expected value of this infinite horizon cost, where you introduce this discount factor. Once more, this is maybe a bit surprising for us when we do optimal control or model predictive control. Often we don't have this gamma. Why you have it? Well, you can bring really good reasons for having it. You can really bring good reasons for not having it. The easy explanation is it's simpler to work with it. And it's cheating. Yes, it's cheating. In MPC, we don't use it because if you use it, it's hard to prove stability. So that's also cheating. Let's just be aware of it. And then it's fine. It's not a big deal. You can also have algorithms without this discount factor, but then you need to be a bit careful about things going to infinity and so on. So it's just a little bit more complicated to discuss. So then what you do is that you do sampling. So here, for instance, we can represent the cost with white where it's lower cost and darker where it's higher cost. And instead of trying to compute this object here numerically or sort of in a standard way, you just do sampling, for instance, Monte Carlo. Okay, so this figure sort of depicts it. You just propagate some trajectories, sum it up, and you have the empirical expectation, and you work with that. You don't only do Monte Carlo, but that's the detail here. So there's one more thing. So Markov decision process is then essentially stochastic optimal control. You want to find the policy that minimizes this return or this cost, actually. Now, this is an infinite dimensional problem. You need to find for all possible policies, right? Search for all possible policies. What people do in practice is that they parameterize the policy somehow with some parametric form, and then the parameter is finite dimensional. We are back in spaces so we are easy to work with, and so then we have a finite dimensional problem. That's an approximation, but that's fine. I'm really simplifying things a lot here, but it's just to give the idea, the principle. All right, so what you do is that you approximately solve this MDP, and this is the important thing in a sample-based fashion, because this is important because it makes what is complicated, makes it simple. Then you get other difficulties somewhere else, but yeah. So then objects that are commonly used are value functions. So the definition of a value function is the cost that you will incur from here to infinity if you start in a given state and then apply a given policy. This is a familiar object from dynamic programming, but if you want to use that to optimize a policy, you need a model. You need to predict the next state. So what people do in reinforcement learning, if they use value functions, is that often they actually use the action value function. So the action value function is the same thing, but you also fix the first action, okay? And now, if you want to improve your policy, you don't need to predict the next state because you already have everything encoded in here, what you need. You just minimize this object with respect to the action and you get the policy. Now, of course, then the question is how you learn this, but that's another story. And then there's this advantage function, which if we use costs instead of rewards, now we should call it a disadvantage function, but that's a detail. It's just the difference of the two. It doesn't matter. Here, I just want to mention it because it appears in some algorithms, okay? It's not important in this talk. And the principle is the same. You just shift it by something that does not depend on the action. So if you want to improve the policy, you can as well use the advantage function. And in some cases, you can prove it's beneficial because you reduce the noise, you reduce variance. All right, and then the optimal ones, I denote them by star. Okay, so how does reinforcement learning work? Well, you need to carry some approximation of some of these functions. And in Q-learning, you try to fit your function approximator to the optimal Q star. Now, how you do that? Of course, if you knew Q star, why would you fit Q theta to it? You use Q star and that's it. Okay, so of course you use a proxy for this. Typically, you do well. You could do Monte Carlo or in temporal difference methods. Well, you use the Bellman equation to replace this, but that's again too detailed here. So the idea here is that if the fit is good, then the two policies are not too different. And at least they are not too different according to the metric you care about, which is the one encoded by the action value function. So even if they are very different, they don't yield a different cost that is very different. And then there's another family of methods, which is policy gradient methods, in which you directly estimate the gradient of your return, or in this case, the cost. And you try to bring it to zero. Once more, how you do that? Well, you use the policy gradient theorem. It's a long story. You can do it. The point here is whatever you do, you need to carry some function approximator of some form. Okay, you need to approximate either a value function, a policy, both. And what people often do in reinforcement learning is to use neural networks, and that's completely fine. It worked really well in many cases. The issue you have with it is you learn the weights and biases of your network. Would you sit in a car, or would you cross the road in front of such a car? I mean, if you're in the US, probably it happened to you, but I don't know, maybe we can do something a little bit safer. So the issue is that you don't know what's happening, right? You plug in something, you get something out, and you don't know if your car will suddenly decide to drive off the road for some reason, or decide that, yeah, killing a pedestrian is expensive, but we can afford it. I don't know. So how can we encode this thing that you shouldn't kill pedestrians? Well, you could say, well, there's some states that are forbidden, so we could say there's a feasible set. We have a bunch of possibly nonlinear equations that say, well, we are good when these are non-positive. And then you could say, well, I assign infinite cost whenever I violate these constraints. But so mathematically, it's completely fine to do this. But then when you sample that, you get infinity and goodbye with everything in your algorithm, right? So what you do is that you put a very large penalty, but how large? And what can you guarantee with that? So in practice, this might work just fine, by the way. I mean, sometimes we are also obsessed with proving things, and then we don't manage to do things because we want to do them perfect. But still, if you can provide guarantees, maybe you should try to. That's our point of view here. Not saying it's easy, though. There's also other things that are hard to encode in terms of a cost. Suppose you want to say, I want my policy to be stabilizing my system. How do you encode it in the cost? It's really non-trivial. By the way, I didn't say it, but please interrupt me, ask questions throughout, because if you miss a point here, it's useless then to carry your doubt until the end. All right, so just before proposing the solution, in summary, well, we have some methods that optimize the policy indirectly by learning value functions, some methods that directly minimize our cost or maximize the return. And typically, well, nowadays, deep neural networks are the most common choice, but they're not the only one. And the good thing is that you get optimality for the true system. When you do MPC, I hear often people saying, MPC is great because it's optimal. Well, first of all, if it's tracking MPC, you don't even know how to select the weights of your matrices. What do you mean optimal? Everything is optimal then, right? Give me the solution, I penalize deviations from it, and then it's optimal, but it's meaningless, right? Sure, you can do economic MPC, where your cost does not penalize deviations from a steady state, but say you have a chemical plant, you want just to maximize revenue. That's why it's called economic, but also minimum time is economic MPC. But then you're optimal for the model, not for the true system. Your model is bound to be inaccurate, so goodbye optimality, right, in a sense. Here I put optimality in quotes because still we are doing function approximation, so we are approximately optimal, but at least we remove one source of inaccuracy, which is the model. The issue is it's difficult to provide guarantees. And so what we propose is something that looks a bit crazy. We want to use parametric nonlinear programs as function approximators in RL. And well, this looks like we are introducing useless complication. In part it is true, but what we have in mind is NLPs that come from model predictive control. The reason for that is that, well, if you combine MPC and RL this way, first of all, RL gives you a way to tune MPC, right? So you say, I want to minimize distance from a given reference, but I also have some other cost that I want to optimize, which is maybe not easy to translate into a cost that MPC likes. Well, you could use RL to tune the quadratic cost of MPC. And then that could improve your closed loop performance. On the other hand, MPC has structure and it gives you some explanations. You see that you take this control action because that will happen in the future. That's what you at least think will happen in the future. And you can now discuss stability and safety with MPC if you do things in a proper way. So, but can we do that? So first of all, about MPC, I don't want to take for granted that everybody knows it. So what does MPC do? Well, we minimize some cost. Here I write it in discrete time as also in reinforcement learning. So you have an initial state. So you're now here X and U are the predictions, okay, to distinguish them from S and A, which are the actual ones. So this is your initial state constrained to match S. Then you have some model. Here, if you read it like this, it's probably a deterministic model, but it doesn't have to be. It can be set valued. It can be a stochastic model as well. And then this is the nicest thing, probably. You can enforce constraints, right? So you can say killing a pedestrian is forbidden. That's really infinite cost. And then, well, we usually have these terminal cost and terminal constraints, which are there to guarantee recursive feasibility and asymptotic stability, typically. So what we get out of this is a sequence of control inputs and states. And so our optimal policy is just the first input, so U0 star. And that's a deterministic policy. If you like a stochastic policy, you can make it. I'm not going to detail it here, but it's possible. So where do these guys come from? You see here I wrote theta, which is a parameter that then I would like to optimize. So typically the model is coming from system identification, right? Or you assume you know it somehow, often from first principles, but it doesn't have to be. And so typically you don't want to touch this, even though I will show you an example in which we can touch parts of it, but in a constrained fashion. Because if you start touching the model, then the meaning of your constraints changes a bit as well, right? The constraints are also usually given. They depend on the state representation you chose, on the model, and so on. Your stage cost, that's what you usually tune by hand, by trial and error. So this one, well, you could say it's given because if you have it in reinforcement learning, you could use the same. The issue is that sometimes in reinforcement learning, you have really nasty nonlinear, non-smooth costs that are then difficult to optimize in MPC, or you could, in principle, have those. And we will see one more motivation for changing this later. And then you have these terminal ingredients. Usually you want these to describe an invariant set of some form, and these to be some sort of Lyapunov function. So if the model is exact and you have an infinite horizon, which you never have, then you have asymptotic stability and optimal performance, but you never have this. So in the best case, you have some form of practical stability and you have some degree of suboptimality. And so the idea is that you could modify theta, in principle all of it, but maybe you want to be careful with parts of it, so maybe the model you want to keep it fixed here, or maybe, so we will see later a bit. So you could adapt theta, but impose safety and stability constraints, and I will show you how you can do that. So then you could recover optimality for the true system and not just for your model. So, but now I showed you how we can get a policy, but what if we need a value function? So first of all, we said the policy is not a problem. We obtain it. We don't have a closed form, right? We might have to solve an optimization problem for that. So but that's okay. We can do it. We can do it in real time. So it's not an issue. We can evaluate it. So that's fine. We obtain a value function if we take the mean instead of the argmin. So that's the optimal cost. And if you want the action value function, you can introduce this further constraint here, and then you have it in principle. Mathematically, this is fine, but be careful, because if you do this, you will get very likely some issues with constraint qualifications. So it's easy that some of your constraints can become linearly dependent, in which case it's hard to solve your problem and so on, but the fix is easy. Also, we usually write this constraint for all k, including 0. You should never enforce inequality constraints on the states for the initial state, because the initial state is fixed. So if you violate it, you immediately are infeasible and so on. You can get, again, LICQ issues. So long story short, be a bit careful with your formulation, but there's nothing wrong in it. The thing that is maybe a little bit surprising is that you can actually differentiate pi, v, and q. They are piecewise differentiable, at least. So you can differentiate them with respect to theta, which is what you need in RL. I didn't mention it before, but RL usually requires derivatives with respect to your parameter theta. And it turns out that the requirement for being able to differentiate with respect to theta is essentially, again, LICQ plus a few other conditions. You could boil it down to if you can solve the problem, you can differentiate it. It's not precisely like this, but almost. And even differentiating the problem is cheaper than solving it. So it's one of these weird cases in which evaluating the function is more expensive than differentiating it, which is usually not the case. All right, so MPC has all the properties required to construct a function approximator. So in principle, we can say let's let RL learn the best theta. So let's now compare MPC with a generic approximator. So as I said here, we have a plan of what will happen in the future, and in our opinion, this is helpful to promote explainability. Here, you don't know anything. You just have an instantaneous feedback. You can handle restrictions on the states through constraints and also on the inputs. Here, you cannot. The good thing here is that neural networks are universal function approximators. So in principle, you can capture these functions as accurately as you like, okay, in the limit exactly. But here we say the model F is bound to be inaccurate, so can we actually recover those functions? That's the first question we ask, because if we cannot recover those, then, well, it's a bit disappointing, right? So we worked on it, and so we wrote MPC with the same discount factor as RL for this proof first. And the result says that actually you can just act on the cost to recover the optimal functions for all the states in a set in which your optimal value function remains finite over the predictions of the model. So this is a bit of a technical requirement. So if this is the set where V star is finite, the set S might be a little bit smaller or much smaller depending on the cases, but essentially it's the set in which if you start here, you remain inside the red set, okay? Now this might look maybe restrictive, technical. Okay, let's try to make sense of it. If gamma is 1, essentially it requires that you are stabilizing in the deterministic case, because otherwise you'd diverge to infinity, right? Or if you have constraints, it requires that your model will not violate them, essentially. So it's not such a horrible requirement. If you have a discount factor, you might even you might even diverge with the state, and your value function might remain still finite. So it's not even such a strong requirement. So this is good news. It means that under mild assumptions, so essentially you can imagine if your model is not too wrong, then you're good to go. It's good news because it means we can use MPC as a function approximator. So the idea was not self-defeating to begin with. Now, how do we guarantee stability? I will discuss it in the simplest case of deterministic systems, which is maybe also not so interesting, but it allows me to keep the discussion a little bit simpler and convey the main idea. So this is the MPC scheme. I removed the discount factor because otherwise we are not able to prove it in a simple way. So what we want to do usually is to find a Lyapunov function, and we want to use the cost, the optimal cost. So the value function should be a Lyapunov function. The issue is that for that, the standard assumptions are that the stage cost is lower bounded by a k function on a compact set, and that your discount factor is 1. And typically neither is satisfied in reinforcement learning. So let's look at the first thing. When this is not satisfied, we have what we call economic MPC. We studied it in the MPC community. It turns out that the condition for stability is called strict dissipativity. So that means that we must have a storage function lambda such that this object, which is called the rotated cost, is lower bounded by a k function on a compact set. Now, this is not very practical for economic MPC because finding storage functions is as hard as finding Lyapunov functions. So it's a nice theoretical development that for MPC is unfortunately not solving most of the practical issues. But here, actually, we are in a nice situation. So first of all, here we could, instead of using the original cost, learn the rotated cost. And if you put this in the sum, you see you have a bunch of terms that cancel out. You have a telescopic sum. The only one that survives is the first one. So what we could do is to use the rotated cost, which is now lower bounded by a k function, and also learn a storage function. So what happens in this case? Well, if we force our rotated cost to be positive definite, then we enforce asymptotic stability by construction. And what happens is that if we don't manage to find a very accurate storage function, then we will give up a little bit on optimality, but at least we have asymptotic stability. And then for the second issue, the discount factor, it turns out that under the same condition that we had before, we can prove that there is a cost modification such that we can have an undiscounted cost that gives policies that are optimal for the discounted MDP and also the value functions. So essentially, here we work really at the MDP level, and you say, well, the discounted MDP has an undiscounted equivalent one. So in fact, we could apply this result, because this one holds also for gamma equals 1 if the original reinforcement learning problem has gamma equals 1. And so we can just apply this result. So in fact, what this says is that we can just forget about the discount factor. We can just have a discount factor in reinforcement learning and have just gamma equals 1 in MPC, and it will work.
I'm a little bit confused about what is being learned here. So,
yeah.
Correctly that you are learning the terminal costs. Do you think they're parameterized?
So, the terminal cost is, I think, in principle, yes, but the issue is the following. When you have a horizon that is not too short, which is so often the terminal cost has little impact on your actual predicted trajectory, right? So if you try to learn that, the sensitivity of your value function and policy with respect to the terminal cost is extremely small. So it's very hard to learn it. But actually, you don't want to learn it because that's an important ingredient for stability, right? So what you rather want to do, I will show you in a simple case what you can do. And in the general case, it's complicated. We know it. In general, nonlinear MPC, it's an open problem, right? How to compute this terminal cost. But let's say we have, at least we know how to cover some of the cases if you have knowledge about the problem, right? But you can compute this as a function of this and that, right?
Under the stage costs L, I see they also parameterize.
Yeah. You learn those. They are known for reinforcement learning, but or actually, you can evaluate them in reinforcement learning. They might even be unknown. So suppose you do some stock exchange, right? You don't know the cost, or well, no, actually you know the cost, you don't know the model. But so essentially, you just need to be able to observe it, right? Say you play Atari games, you don't necessarily know what gives you points, but you know that you got points, right? So, so you learn in this setting, you learn this and that. So this is a bit of a weird thing. It's an initial cost, right? It doesn't affect your problem, but that's what makes the trick. So if you want to know more about this, you can learn something about economic MPC. You find all the references there, and also we explained, of course, in this paper.
Would you also explain again what is this difference between S and V?
So, yeah, the science set is the set of states for which your model prediction gives you states for which V star of X is finite. It's a bit technical. It's hard to make sense of it. But really what it means is that your model is not completely off. And it can even be completely off and you might still manage to find such cases. But yeah, in general, if you have a, let's say if your model is decent, then this set S is non-empty because that, like you could say, yeah, nice construct, but what if S is always empty, right? So yeah, in practice we saw if your model is not too wrong, then this works. Well, it works. Once more, we never know the optimal V star, pi star, Q star, but learning is successful. At least you improve. That's what we observed. And in some cases, you can really show that you do get. So when you know them, you see that you do get the optimal ones. But these are special cases. Right, now about safety. I think I need to hurry up a little bit. So about safety, I think our point of view is that using models is the most natural way to capture constraints and to capture rare events. Constraint violations are rare events, especially when you learn how to satisfy them, right? This is not only our position. There's also, companies doing safety certification. They also claim models are the only way to do it. In fact, also when you do reinforcement learning model free, you don't just take a car, let it drive, destroy the car in the best case, right? That would be a bit expensive. So, or plug it to a chemical plant and wait until it explodes. It's not really what you want to do, right? So you are using a model anyway. But if you manage to use it to predict also the uncertainty, you can account also for the correlation in time. So your samples give you more information, you make better use of them. And I just want to bring you a very simple example here. This is a linear scalar example, one state, one action. No action, sorry. Here in gray, you have 10,000 trajectories. In dashed black, you have the exact propagation of this uncertainty. If you try to first estimate a nominal model from these trajectories with just least squares, which is not maximum likelihood, and then for the uncertainty, you take the worst case of the error, and then you propagate it, you get that you essentially recover the black lines quite accurately. So the estimated model error is this small, while if you take the samples here, you see you have a big underestimation of the true uncertainty. Some people say, well, if you are robust, you're conservative. Well, I claim no, because here for very short horizons, you're quite tight. So you want to be careful that you might end up here, even though it's super rare. And then you adjust your policy as you go. That's what MPC does, right? But when you're close, then you account for it. But if you just assume that this is your uncertainty, then you might end up here, right? It's maybe 1e to the minus 6. Sure, drive a little bit around. How many miles we drive every day? Sooner or later, you kill someone, right? Also with this, you will kill someone because you can never know your exact uncertainty. That's a long story, but my point of view is that if you can quantify your uncertainty, you should do it properly as well as you can and not just neglect things. Then, of course, you might have other applications in which you don't care so much, and then it's completely fine to accept constraint violation. All right, so in this case, the model is a set. You need to predict a set where the next state can be. And so you have the usual issues. You don't know the shape a priori. You might fit an ellipsoid. You might use polyhedra. Usually it's a choice out of convenience, what tools you have, what tools you know, what you think is best suited. Now, which criterion do you select? Well, if you do a set membership system identification, usually you minimize the volume of this set. And that's completely reasonable because you don't know what you will use it for, right? So then you try to make it small. But here we know we want to maximize closed loop performance. And that might mean that we want to know the set very well here, and we don't care so much down there because it's in a safe configuration. And the thing is, we need simple representations because we need to solve the MPC problem in real time online, right? So safety has a price, which is computational time. So the idea could be, well, we could adapt, say, move these planes with RL as long as they contain the red set, right? The issue, of course, is that you don't know the red set. Otherwise, you would have solved your problem. You only have samples. So as I show here, you're bound to be optimistic. Now you can think of ways to counter that, but this is a fundamental issue. You can never have probability 1 of including your set that you don't know. So now one question is, what's the probability that one sample falls outside? That's food for thoughts for future research. So just to say, we have not solved all the problems, especially not the unsolvable ones. There's a lot of stuff to do. This is just one possible approach towards this. So in practice, the engineering approach would be, well, you overestimate this set, collect data, then when you're more confident, adapt it. Now, of course, the thing is we should think how to do that in a principled way, and that's where I don't have an answer yet, but what I would like to work on in the future. And I want to conclude with one example, because now it's a lot of theory and a lot of abstract concepts that you might think are hard to use in practice. So here we have a linear system, and we have some, so we have a double integrator for simplicity, box constraints, just a hypercube, no, a cube actually, we are, yeah, anyway. And so we don't know the noise set W in which our process noise lies. So we approximate it with some polyhedron. And what we learn is these parameters. So we have this matrix that defines our noise set. So we are allowed to rotate these planes. And then the cost for RL is something that once, maybe I can show. So the cost wants to bring us down here, right, somewhere. But we cannot, we have a constraint here. And we want to satisfy the constraint under all possible circumstances. So here we have a quadratic cost that penalizes deviations from a reference. So we want to learn the reference. We want to learn the matrix, the stage cost matrix H. Here, for the terminal cost, from your question, this P is given by the Riccati equation. So it's a function of my parameters. And this is the initial cost I showed you before that we have for this economic thingy. And this is constraint tightening. So this approach is the one described by Kishi in his paper 2002, I think. And then this is a robust positive invariant set. Again, these are functions of our parameters, okay? So we learn them, but indirectly. So what do we do? If we do Q-learning, we solve a problem that is now constrained. So here we minimize this. Take care that this is not the temporal difference error that we minimize because we fix this parameter. It's called fixing the target. If you don't use theta minus, but just theta and optimize over this, you get something wrong, okay? It's again a long story, so you don't minimize the expected TD error. You minimize something else. That's why they call it semi-gradient methods. And then we have some constraints. So our steady state must be a steady state for the system, for the nominal system. Our stage cost must be positive definite. And here we have a bunch of samples in our data set, and they must all be contained in our polyhedron. That is the uncertainty description we have. And our terminal set must be non-empty. And then you solve this problem at every RL step, and you update your parameter with a learning rate. All right, so if you do this, I can show you the video. Here we start here. The red polyhedra are the tube along the prediction. And this yellow set is the minimum robust positive invariant set to which we are guaranteed to asymptotically converge. This circle is the reference. We started at the origin. This science set is our terminal set, and these are our constraints. And as I said, we want to go as close as possible to -3. And here, the true uncertainty set is the octagon, but I don't know it. I only know some samples. Here, I start with a set populated by some samples. The red ones are the convex hull. Actually, I can throw away all the others for what I want to do, because if the red ones are contained in the polyhedron, then the others must be, just to save some memory. And we start with this initial guess, just some planes thrown there and, made tight on the samples. And now what we do is that we let the system evolve, and every 20 samples, we do a batch update, Q-learning style. So you see now it's learning that we can move the reference a bit to the left. It's not touching this set because we don't touch any constraints, so it doesn't matter if we change the shape here. And now we approach the constraint, the terminal set starts to change. And now that we touch the constraints, you see now it's learning that we need to know well this part of the uncertainty. We don't care about this part because this is safe. And on the way here, it's adjusting also the stage cost, because the stage cost produces also the linear feedback used to generate the terminal set and the minimum RPI set, and the constraint tightening. And the constraint tightening is done such that the minimum RPI set is contained in the box. So by changing the cost, changing the feedback, we are able to change the shape of this minimum RPI set in a way that is actually non-trivial. We wouldn't know how to do it, or I wouldn't know how to do it, actually. And so we are really learning how to change this cost and policy to get as close as possible to this bound, while remaining always safe. And, well, maybe you see it better if so maybe, here we were already at the constraint, and if you see from here to here, not much changed, but this set became a little bit, narrower, so we could get a little bit closer. All right, so just to conclude, from the point of view of RL, usually we use generic approximators, and it's hard to incorporate knowledge about the models. People sometimes do imitation learning first, but that's one extra step. And as I said, it's difficult to get these guarantees that we like. So MPC is a structured approximator, function approximator that can fix this issue and also make it easier to include some prior knowledge you might have on your model, or even some prior controller that you might have on the system. On the other hand, you have MPC, where you directly exploit knowledge on the system. You can have safety and stability, but where your performance depends on the model accuracy. And sure, you can improve your model and do system identification, but at some point you reach some limits. First of all, it's hard to learn accurate models. So SysID is getting increasingly more difficult, and then you need to solve the problem in real time. So if you have a super complicated model, you will not make it. So you have limitations in just improving the model. So actually, with RL, you can improve other components of MPC. By the way, here we were learning, this is the model, right? It's part of the model, but we are learning it subject to some constraints, of course. So we are also learning part of the model, but not the nominal one, for instance. So RL gives some ways to tune MPC, which is an open problem today. And yeah, it's not the same as system identification. Actually, in some sense, you can show they are orthogonal, because if with a wrong model you manage to recover the correct policy and the value functions, then there's some orthogonality. All right, so this is what I just said. Actually, one important thing is that you can also do safe exploration. I didn't touch upon this point, but since you have constraints, if instead of taking your policy from MPC and perturbing it, you perturb the cost of MPC, then if the cost pushes your initial input towards a constraint, you will still not violate the constraint. So you can do exploration in a safe way without worrying, which is also a nice feature. You have also some other opportunities. Well, since the parameter space is typically low dimensional, you don't have usually millions of parameters, right? You could even do second order methods and maybe get faster learning. As I said, the sensitivity computation is cheap. It's cheaper than solving MPC. So if you can run MPC in real time, you can also differentiate it and solve RL on top of it. The RL problem becomes constrained, so I think there should be some work done to check how to best formulate this problem. I also think that we need to work a little bit more. So when I started working on this topic, I thought, oh, but these guys in RL, they don't care about safety and stability. And then I started thinking, yeah, okay, how can we prove stability for a stochastic system? If you look up the literature, I would say there's still a lot of work to be done on our end as well. So it was easy to complain about them, and then now I'm complaining about ourselves as well. And then, well, I know Seb worked on some realistic examples. I didn't have the chance to do that yet, but yeah, I would like to find some nice use case where we can apply this. Yeah, thank you.
All right, great. Our final speaker is Dr. Roberto Calandra. Unfortunately, he had... So, as I was saying, Roberto cannot join us. He had a sudden issue, so despite he wanted to be here, he couldn't be. So he sent us a video so that we're going to play. It's not a long talk, but it's very interesting. And just quickly introduce him. Roberto is now full professor at UT Dresden, and before he worked at Meta AI in California. He was a postdoc in Berkeley, working with Professor Levine. Actually, him and I worked together at the lab of Jan Peters when during his PhD, and he has done a lot of amazing work. So please, let's stay for this final talk, and if you have questions, of course, you can contact Roberto.
This was a big competition hosting some of the best robotic team in the world. And what we can see here are team spending years, up to 100 times, 100 people working on having humanoid robots solving tasks like walking uneven terrain, opening doors, turning valves. And fundamentally, from this video, we can see how all of these robots are catastrophically failing in a way that we would never associate with intelligence, that we would never expect a human to fail. If we think, for example, at kids, no kids would ever think of trying to turn a valve and instead falling down because they miss it. And so one of the problems that I'm fundamentally interested in answering is, what are we missing? What are we missing before we have robots that can meaningfully interact and help people in the real world in a way that is useful, in a way that is adaptive, in a way that is safe? And of course, there are many challenges in order to be able to one day reach this goal, all the way from how do we build the hardware, the type of sensing that we provide, all the way to how do we do high-level planning and quick adaptation to new tasks. And as a machine learning person, of course, the answer to some of this problem will, from my point of view, have to leverage some of the tools that the machine learning community has been building over the last decades. And in particular, in this talk, I'll be focusing in reinforcement learning, which is one of the topics that we work on in my lab. And specifically for the rest of the talk, I will be discussing 4 different topics, which also encompass different paradigms of how people have been trying to deploy reinforcement learning in the real world. And I will start from looking into data efficient learning and specifically model-based reinforcement learning. Now, for people that are already familiar with reinforcement learning, the large majority of algorithms that people have been using in the reinforcement learning community so far are so-called model-free algorithms. These algorithms are convenient for several reasons, including the fact that you typically have some type of local convergence guarantee. They are typically very simple to implement and computationally quite light. However, the main drawbacks of this type of algorithms is that they do not typically generalize to changes in the environment or in the task or the robot. And at the same time, they can be extremely data inefficient, often requiring millions or even billions of interaction with the environment. The other type of big family of reinforcement learning algorithms are the so-called model-based. Model-based algorithms draw a little bit of inspiration from humans, where we are able, for example, to predict the effects of our actions. But from a machine learning point of view, model-based algorithms do not possess at the moment strong convergence guarantees. They can be more complicated in terms of infrastructure in order to be able to learn accurately model. And they are often very computationally intensive because of the planning which is executed. However, at the same time, model-based algorithms are sometimes very convenient because they allow us to generalize to new tasks, and they can become extremely data efficient, typically several order of magnitude more than model-free. And a fun fact is that we do actually have evidence from neuroscience that humans seems to be using both approaches, and this is, of course, a very interesting venue of future research. Now, if we look at the way that model-based reinforcement learning typically work, what we typically have is that we have 2 different phases, where the first phase is the learning of the dynamics. This would be the equivalent of a forward dynamic model, where we want to learn a model, f tilde, which, given the current state and action of the system, is going to predict what's going to be the next state. In the moment when we then have this model, what we typically happen is that we are now going to use this model to do some sort of planning or the optimization of the controller in such a way that we can, at a high level, imagine to obtain a controller pi, which we can then go into the real world, apply to the real robot, and eventually get a set of tuples collected from the behavior of the robot of the state, action, and corresponding reward, according to the standard Markov decision process formulation. Now, our small contribution to the field of model-based reinforcement learning algorithm was in 2018 the introduction of PETS. PETS was the first algorithm that proposed the use of deep learning models and specifically probabilistic neural networks in the context of model-based reinforcement learning. And the idea here is that we want to learn a forward dynamics model using an ensemble of different probabilistic neural networks. We are then going to project into the future this uncertainty by producing distribution over the trajectory. And once we have distribution over trajectory, we can then apply model predictive control and keep replanning trajectories as we go and move over time. These algorithms showed to work very well on medium-sized problem, and in fact was competitive in terms of both data efficiency and final performance. So here we can see several videos of simple simulated tasks being solved within 100 trials. And in comparison, traditional model-free algorithms would instead take millions of interactions and trials to achieve the same performance. Now, this same algorithm can here is as an example, on the left is our algorithm SPETS, which already after 15 trials is able to walk. At the center is a competing model-based algorithm. And on the right was the state-of-the-art of model-free algorithms at the time. And after 50 trials, our algorithm was already able to run very fast, while model-free algorithms had only just started. Now, this same class of algorithms can also be applied into the real world with a little bit of code optimization to make it fast enough. And here was an example of learning how to fly with a quadcopter, where the idea was that we wanted to stabilize the quadcopter by controlling directly the PWM signals sent to the individual motors. And in this case, the quadcopter is drifting because of IMU, but the goal was only to stabilize its axis to keep it horizontal, which was successful. And in practice, it was possible to learn such kind of behavior within just less than a minute of data collected to the real world. Similar algorithm can also be extended to be conditioned on external variable, and by training such a latent variable model, we can in practice also adapt to different payload where the system is able to implicitly understand that there has been a change in the dynamics of the system and can then adapt to the dynamics model on the fly to these specific changes in condition. And also in this case, this seemed to be working extremely well, very robustly, and we were able to pick up different payloads with the different weight and dynamics of the rope, different length of the rope. Now, over the years, we also investigated several fundamental questions to really try to understand and overcome some of the limitations of model-based reinforcement learning. From asking the question of whether accurate models are a condition necessary for good control performance, to asking the question if accurate models is a condition sufficient for good control performance, to looking into how we can avoid the multiplicative error of the recursive one-step prediction, which is typically employed in this type of forward dynamics model propagation in order to predict a whole trajectory or distribution of trajectory. And finally, how can we dynamically tune the hyperparameters of model-based reinforcement learning in order to achieve the best performance. And as you know, hyperparameters are a crucial aspect of all modern machine learning models. And so here we can really do great progress in terms of performance by smartly tuned hyperparameters in a dynamic way. Now, I do not have time for going through all of these works, but I wanted to dig a little deeper into whether accurate models is a condition necessary for good control performance. And the question here is really, are accurate model conditions necessary? This is typically a sort of interesting question because in this two steps type of optimization, what we typically see is that we first optimize the dynamics model and only after we use this dynamics model. And so what we did here instead is to optimize the dynamics model, which typically is optimized with respect to the likelihood of the next state, and instead directly optimize it with respect to the final reward once this dynamics model is plugged into the controller, into the policy. And in practice, with the machinery that was available at the time, computing gradients was analytically intractable. And so we instead decided to use a zero-order optimizer, namely Bayesian optimization. And we did this into the LQG framework. So once the dynamics model was learned, it was actually used in a LQG. And so the results were very interesting because they demonstrated that in practice, yes, it was possible to achieve performance that were quasi-optimal, typically over 95% of performance. But at the same time, these performance were in practice caused by dynamics models that were unrealistic, that were not physically grounded into the problem that we were sort of trying to solve. And in the case, for example, of Dubin cars, what we can see is that the cost function, we are able to find cost function with the blue dot here at the top right that are extremely close to the optimal, which is this sort of ridge that we see going from the bottom left to the top right. However, at the same time, the sort of parameters that are identified by the algorithms are not grounded in reality because they are sort of far away from the real parameters, which would be at 1,1. And this really from my point of view, opened the question of, what is a useful model? Because there can be entire classes of models that are useful, although they might not be correct in the traditional sense. And this is, of course, problematic in terms of generalization to changes in the environment or to different tasks. But if we only care about the performance on a single task, we might actually be able to get away with achieving very high performance really fast without caring about the grounding of the dynamics function. And an example was some experiment that we did in the real world with a quadcopter. And what we saw in this experiment is that our learned controller, after just 60 trials, was able to beat the nominal controller provided by the producers of the quadcopter by increasing performance over 10%. Now, another very interesting topic that I want to discuss a little bit more is whether accurate models is a condition sufficient for good control performance. And our sort of contribution to this was the introduction of the concept of objective mismatch. Now, the idea is that when we learn the dynamics model, we typically optimize with respect to the negative log likelihood of the data. However, in the moment when we then use this dynamics model for planning and optimize, we instead use a different objective, which is the task reward. Now, objective mismatch, by definition, is the mismatch that arises when one objective is optimized in the hope that a second, often correlated metric will also be optimized. And this is exactly the case that we have in traditional model-based reinforcement learning, because when we are optimizing the dynamics model with respect to the negative log likelihood, there is a valid sort of point to be made that maybe this is not going to be indeed optimizing the task reward, which is what we care, which will sort of be in this second phase. And to test this hypothesis, we evaluated many different models, and we tried to compare what is the relationship between the log likelihood of the dynamics model and the task performance. And to our great surprise, what we can observe is the fact that indeed we do not always have a strong correlation between performance of the reward and sort of accuracy of the model. And this is very problematic because traditionally people have been thinking that if we just get a better model during the first phase of optimizing the dynamics model, we would then automatically achieve better performance. But this is actually not the case. The main reason is sort of deep, and is the fact that unlike system identification, in model-based reinforcement learning, we typically are constrained to a very small subset of the state action space. And during this learning phase, because the likelihood is depending on the density of the data, we might effectively be learning very well part of the state action space that are not so relevant to the task afterward. And as a result, this is also prone to generate adversarial situation where we might be able to optimize the sort of the reward in a negative way, but at the same time keeping the same likelihood of the data by just nudging the model sort of in the wrong place and producing large deviation into the final trajectory. Now, in some cases, we want to deal with robotic systems which are ill-defined, that are very difficult to fully sense and to fully control. And in this case, an alternative approach is the use of Bayesian optimization. Bayesian optimization is similar to model-based reinforcement learning in the sense that we are learning also a model of our system, but this model of our system is not a forward dynamics, but is instead a response surface that directly map parameters of our controller to expected reward. And in the moment when we have this reward, we can then optimize the parameters and choose which set of parameters to evaluate next. And when applied to real robot, this can actually work extremely well. So here are some videos from an experiment that we did many years ago of a quasi-passive dynamic walker trying to learn how to walk. And initially, the robot was not able to learn, but as we progress over trials, the robot is improving the performance. And after just 60 trials, this robot is basically able to achieve maximum performance of the system, matching performance that required up to 2 years for a student to manually tuned. And in practice, this was achieved within a day of experiment, and the final result was extremely robust. Now, the same type of algorithms can also be used in cases that are not just single objective optimization, but for example, multi-objective optimization, where we now have multiple potential objectives that we care about, such as speed and maybe how much power we are using for walking. This was a simulated experiment on a model of a micro robot, but overall, we've been applied Bayesian optimization over a very large number of tasks in sort of over the years, from learning to walk, to learning to fly, to controlling ferrofluid droplets to move potentially inside the body of people one day. And I would strongly recommend Bayesian optimization as a very robust solution when optimizing controllers in low-dimensional spaces, because it's very capable of dealing with the uncertainty and noise of the real world. Now, the third paradigm that I want to discuss today is self-supervised learning. With large modern deep learning models, the scale of the data, how much data we have, is often crucial to learn complex relationship and complex models. And in many cases, we don't have the capacity, or we don't have the will to have a human in the loop collecting a large number of experiments or labeling this type of experiment sort of all day. And so the idea of self-supervised learning is twofold. On the one hand, the fact that we want to have models that are trained without human labels, but also the fact that we want to collect this data with minimal human intervention. And this really means, and in many cases boils down to the fact that we want to design our experimental setting very carefully as to minimize the need for human intervention. Now, one example of this type of model, self-supervised model that we trained in the past, was a stability model, action conditional model that was able to basically predict the stability of grasping an object, condition on what actions we would take next with the gripper. And what we did in order to be able to collect enough data to train this large model was that we set up a self-supervised data collection process with a 7 degrees of freedom arm and a parallel GeoGripper, where we basically just had to put an object in front of the robot, and the robot would identify the rough position of the object and would attempt to grasp it. And after attempting to lift it, would basically predict from the fingertip whether the object is still within its grasp or not. And by doing this, we were able to basically keep collecting data continuously with minimal human intervention. And once every few hours, somebody would just pass by in front of the robot, change the object, and the robot could keep trying to grasp it on and on and on. And the label, most importantly, was automatically generated without the need for a human intervention. And in practice, we use this system together with over 60 different training objects, and we had the system running almost continuously for over 2 weeks, collecting in total over 6,000 grasps. And these 6,000 grasps were then used to train the model. And from this model, we eventually investigated whether touch is a useful sensing modality when grasping. And we demonstrated that a system with touch was able to grasp successfully unseen objects with an accuracy of over 83%, while only using vision as a sensing modality was able to achieve only 56%. I want to show in particular one policy that was learned on this rubber bear. And what we can see here is that initially the robot is touching a small point that is glued. And in the moment when identify this area of high pressure, it basically, the model implicitly learn how to center it in the fingertip. And once it's stably in the fingertip in the center, it's happy and decide that, okay, this is good enough. I'm going now to lift the object because this is a stable grasp. A similar self-supervised process was also used when learning how to rotate marbles and sort of move marbles within fingertips of a multi-finger hand using tactile sensing. And this is a very sort of difficult task for robot because you really need to be gentle. And in this case, we also automated the process so that the marble was automatically resetted to a place, a location in front of the robot, and the robot would just grasp it always in the same place, play with it, and then drop it. And specifically, the model that we used for learning this task was also model-based reinforcement learning base. So we were taking the images from the tactile sensor input. We were learning encoding into a latent space. And then in this latent space, we were learning a forward dynamics model where we were able to predict how different actions at the finger joints would result in changes into the images. Now, finally, the RAS paradigm that has become popular over the last few years is sim-to-real. The idea of sim-to-real is that in many cases, it's convenient to learn a policy entirely in simulation because we can basically afford to do a much higher number of trials for the learning. And once we have this policy, we can then deploy it in the real world. Now, if this is done in a naive way, as described, it actually does not work. However, what we can do is that we can try to exploit structure of the problem and provide algorithms adaptivity at deployment time. And one way of doing this is, for example, the algorithm rapid motor adaptation, where the idea is that we are trying to learn encoded extrinsic, here defined as Z and Z tilde. And this is learned during the training time in simulation by basically varying the parameters of the object that we are trying to manipulate. And during execution time and deployment in the real robot, the system will try to identify this latent and extrinsic, and then the policy will behave depending on what extrinsic has been identified. And you can intuitively think that this extrinsic might, in the case of manipulation, for example, encode properties of the object that we are trying to manipulate. Now, this actually works in practice extremely well, and here are some videos of our multi-finger robotic hand rotating several different objects that have never been seen before by the system. And this is possible because each one of these objects is actually identified with a slightly different extrinsic that in practice provide information of how do we need to adjust the rotating movement for this particular object. Recently, we also applied the same type of algorithms and sim-to-real approach onto learning how to play piano, and we have preliminary results of the fact that we can basically produce music and movements that are quite effective also in the real world. Now, to conclude, I would like to thank all of my amazing collaborators that work with me over the years. All of the work that I've shown you today would not be possible without them, and I'm very grateful for all of their brilliant minds and their time working together. And to conclude, today I showed you multiple paradigms that have been possible to use for learning onto real robots, from model-based reinforcement learning to Bayesian optimization to self-supervised learning in order to automatize the data collection, and sim-to-real if we instead want to learn entirely in simulation and then transfer onto the real robot. And as a final consideration, the choice of choosing a specific approach and a specific paradigm, it often really boils down to the circumstances of what is the problem, what is the experimental setting that we can build, and how do we want to leverage the structure of the problem in order to try to improve the efficiency.
Roberto couldn't be here, please contact him. You can find his email on his website, and you can ask him all the questions.